Class is now starting. All attendees are in listen-only mode.
Hello, good morning, everyone. It is 9:01, so we are going to get started today. My name is Anna Zylik, and I'm with ICF. We are the vendor working on behalf of Energize Connecticut to bring these passive house trainings to all of you. Thanks for joining us today. We will be recording this training and we'll make this available afterwards for you all. These trainings are at no cost thanks to the sponsors of Energize Connecticut, and we are also in partnership with Connecticut Passive House. A quick reminder that the Energize Connecticut program is offering a 50% cost reimbursement for professionals pursuing either FIAS or FIA accreditation trainings. So this includes the cost of the trainings and the exam. And once you become certified, we'll work with you to process the 50% cost reimbursement. And if you have any questions about the reimbursements, please don't hesitate to reach out. You can go to the next slide, Andrew. And thank you. In addition to the Passive House Training Initiative and accreditation reimbursements, the sponsors of Energize Connecticut are proud to offer incentives to developers of multifamily projects with 5 units or more in the state of Connecticut who pursue Passive House certification. And on the next slide is an image of just the incentive structure offers for pre-construction incentives to support developers in conducting Passive House feasibility studies, energy modeling, and post-construction incentives for projects that receive full Passive House certification. So for more info on these incentives and how to participate, visit our website or contact us via the number listed below. And yeah, with that, I will turn it over to today's hosts, Monte Paulsen and Andrew Steingiser.
Great, thank you, Anna. Good morning. I'm Andrew Steingiser, and I'm here with my colleague, Monte Paulsen. We are from RDH Building Science. I'm coming to you from the Boston office, Monte from Vancouver. And let Monte jump in and just introduce yourself here.
Good morning, everybody. Yeah, I'm Monte Paulsen. I lead the Passive House team at RDH. I'm a PHI accredited building certifier. We've worked on about 7 million square feet of Passive House, so we're kind of starting to get the hang of it. I also teach a workshop called The Pattern Language from Passive House. You can sign up for it if you're interested, from Passive House Canada. And I've been doing this for more than a decade. I was a co-founder of Passive House Canada, of the PHPP user group, the Global Passive House Happy Hour, and a few other bits of mischief over the last decade or so. The picture of me, by the way, it's from 2019 on the subway in Beijing. And I love it because it's just so unfathomable now to be squished in like that in a foreign city with a bunch of people and nobody's wearing a mask.
All right. And I am Andrew Steingiser. Thank you, Monte. I am an architect in Massachusetts, certified Passive House consultant through the Passive House Institute US. I'm leading our Passive House consulting for RDH Boston. I see myself as a bit of a Luke Skywalker to Monte being Yoda. I know some things already from my Obi-Wans, but you know, Monte's a bit of a funny character and learning a lot from our collaboration. So, I'm recently appointed to the Passive House Mass Board of Directors. Really excited to dig in. I've been a Passive House consultant since 2013 while practicing in architecture firms, and after bolstering my design education, really couldn't turn back. Really, I'm just interested in Passive House and high performance buildings at this point, so I'm happy to get my hands on as many projects as possible and high performance projects, and hopefully have a positive influence. I understand most of you are probably in Connecticut. I born and raised in Glastonbury, GHS class of '02, so maybe I have some classmates out there. And this is where I spend most of my time now, on the playground with my two small people. All right, so the agenda for today, yeah, local requirements and incentive programs. We have some great things happening regionally in New England, Massachusetts and Connecticut in particular. Yeah, Monte has a unique insight to what's been going on in Vancouver for the last decade or so, and a lot of similar things are occurring here now. Architects and engineers, we are responsible for adaptation, and we'll get into that. We have a series of case studies of multifamily passive house buildings, both through Passive House Institute US, FIAS, and PHI, the International Passive House through Germany. And we have some information about cost and timeline as well. That's always a point of conversation around here these days. You know, what's that going to cost me? How long is it going to take? A little bit about RDH. So up until a few years ago, I hadn't heard of RDH either. It stands for Ricketts Dell Hubs, company founded in 1997 in Vancouver, and it's grown through British Columbia to Seattle, Portland, Oregon, Oakland, California, Toronto, and more recently in Boston. Our Boston office was established about 5 years ago, offering mostly building enclosure consulting to date, now offering passive house and energy and sustainability consulting as well. We're really a well-integrated organization. I'm collaborating with colleagues all over the continent daily. It's just really quite impressive. RDH takes on renovation and restoration repair, as well as original science research. We have a laboratory in Waterloo, Ontario, where we perform testing for manufacturers on membranes and other materials, et cetera. And we apply what we've learned to practice, to building enclosure consulting, facade engineering, and passive house and energy consulting, which we offer in an integrated fashion, which is somewhat unique to your traditional enclosure consulting firm. We really follow an enclosure first background based in building science, taking a holistic approach, and have become leaders in high performance buildings with 6+ at this point, 7 million+ square feet of passive house and high performance work, a lot of which Monte has touched. So again, we take a holistic approach, integrating building enclosure performance with energy performance for better whole building performance and cost outcomes, integrate climate change adaptation resilience planning in new and existing buildings. We work on numerous large institutional net zero energy and net zero carbon buildings, and currently have the most experience on large building passive house projects in North America. And we're working on 2 of the tallest passive house buildings in the world, both in Vancouver. So we design high performance buildings, and in the process, you know, we're not limited by the technology, but the process. So we flip the process around, where we set the performance goals first and design to meet it, and assist architects and designers in doing so, helping set the targets first and developing the designs to meet them. You know, absolute metrics equal energy budgets to manage. We try to integrate milestones for high performance buildings into the design process, updating energy modeling, thermal bridge simulations, you know, et cetera, throughout in a series of workshops often. And we think a little bit about everything at day one. We have to, and we have to make decisions about where to spend our energy budgets. You know, we talk a lot about key levers that we pull, pull one, it has an effect on another. And so we again, we look at a holistic approach. So a lot of exciting things are happening in New England. Here in Massachusetts, where I'm practicing day to day, Governor Baker last year signed into law decarbonization. Decarbonization is now law in Massachusetts, with targets of the 50% reduction by 2030, 75 by 2040, and net zero carbon emissions by 2050. That is a pretty tall order. A lot of municipalities are taking this on, but how do we get there? Hot off the press, within the last 2 weeks, there was a presentation by the Massachusetts Department of Energy and Resources with a new draft of our stretch code, so-called stretch code, and additional opt-in stretch code for the Commonwealth of Massachusetts, where Passive House becomes a really central piece in the electrification and decarbonization strategies in both residential and commercial stretch codes, and the opt-in stretch codes, which hopefully we'll see many municipalities in the Commonwealth adopting. ICF administers the Mass Save program, through which we have some pretty great incentives currently. There are currently 6,500 plus units of 6-unit plus multifamily passive house projects enrolled in this Mass Save program at various points. There's money there. There's $5,000 on the table to perform an initial feasibility study, like RDH will perform, to assess, the appropriate design targets relative to the passive house standard. And passive house has really taken off here in Massachusetts, and I know is in Connecticut as well. I see emails all the time right before the holidays. I saw many Connecticut multifamily projects being FIA certified through those email blasts. So it's really taking off. This is another slide courtesy of DOER from that presentation, and that Bunker Hill project is actually one that RDH is involved in, a very large development, which we'll show shortly. But many architecture firms are taking on the challenge of designing these passive house buildings. Passive house consultants, architects are becoming passive house consultants. Ideally, clients are too. It really helps when everyone is speaking the same language. So Passive House really provides that common language, which is really in sync with the goals and strategies for achieving decarbonization. In Connecticut recently too, decarbonization was signed into law. And it's interesting, we'll see, it will be all the similar strategies as well. The Connecticut incentives reflecting similarly the incentives in Massachusetts as well. Money for feasibility studies, for continued energy modeling, and then each carrot takes you a little further through the design and energy modeling process, where in post-construction, there's additional incentives per unit that can really add up and help take the edge off of the potentially slightly increased first cost of certain components in a passive house design building. So of course, RDH performs passive house feasibility studies as well. It's basically the first step we take in a passive house design process anyway, and it's great that these local incentive programs are supporting this step as well. It's this point at which we define certain targets relative to achieving the passive house standard. What are the R values of roof, wall, slab? What are U values of window? what is the percentage of glazing that we currently have, and what would it need to be if it needed to be reduced at all, decreasing solar heat gain, things like that. Taking site orientation and shading into consideration, all these things, and we can determine the feasibility of a particular project achieving either the PHI or FIA standard. In this case, this is a screenshot from the WUFI passive modeling, which is software used for FIA certification. So architects and engineers are responsible for adaptation. For those in the high performance building community, there's a lot of talk about adaptation and mitigation. And buildings need to protect human life in an increasingly hostile climate. This is not unfamiliar to many folks. This sort of data, we can see the correlation between carbon dioxide levels and global temperature. Never in the last 2,000 years has the global temperature change been as severe as it is right now, beginning with industrialization because of increasing carbon emissions. So, climate science is 160 years old at least, and there's really no question about what is happening among climate scientists. There's plenty of debate among politicians, bought and paid for by politicians, and a lot of questionable studies out there. But as engineers and architects, we have an obligation to listen to the science and take that into consideration when designing our buildings to protect us from evolving climates. So oceans are absorbing 90% of the increased heat on the planet for now. More than 90% of the heat generated over the last 50 years has been absorbed by the oceans, temporarily helping spare humanity and other land-based species from temperatures that would already be catastrophic. The amount of heat soaked up by the oceans is enormous. Last year, the upper 2,000 meters of the ocean absorbed 14 more zetajoules than it did in 2020. Now, I had a Marty McFly moment there too. I said, what the hell is a zetajoule? But this amount of extra energy is 145 times greater than the world's entire electricity generation, which by comparison is about half a zetajoule, to put it in context. So that's a lot. So, here's a sampling of some recent local reports. Some of the studies there that led to the decarbonization roadmap in Massachusetts, Green Ribbon Commission's Carbon Free Boston Report, among others. And very recently, within the last 2 weeks, this NOAA report on the right with an update on global and regional sea level rise scenarios for the US. So pulling some high-level stats from these reports, we know, for instance, in Boston, 2/3 of the greenhouse gas emissions come from buildings. Statistically, that's often about 40% nationally in the US of the greenhouse gas emissions coming from buildings. So we know that buildings among transportation and the grid are a major piece that need to be tackled in decarbonization. The decarbonization report for Massachusetts actually highlights that particularly 3 steps needed for decarbonization: electrification of space and water heating, investing in the building envelope, which will drive down costs of energy for consumers and the grid, particularly if we level off those peak times, and using decarbonized energy sources, i.e. renewable sources of energy to run electrified buildings, taking the on-site combustion out of the equation, as well as at the grid level. So the information is out there. We know this. The result of our carbon emissions, if we fail to curb emissions, may look something like this. Zeroing in close to home here, among the report released recently by NOAA, they've got a great online sea-rise simulator that you can go play with, and I urge everyone to go check that out. Taking Boston at its worst case high tide mark in 100 years from now, this is what Boston could look like at high tide if we fail to curb our current emissions. Thankfully, we are taking steps to do so, but this could be the most extreme level of result. Regardless, NOAA predicts that even curbing our current level of emissions could lead to about 2 feet of sea level rise on the US coastline by 2100. So resiliency and carbon emissions, again, are tied together. And as we know, much of that is coming from our buildings. So what do we do about that? Local circumstances. So this is not a photoshopped image. This was Boston in 2018, and this messed up my commute that day. I get off at that stop when I was going to my previous office, and yeah, that's the harbor in Atlantic Avenue during a record high tide crest. Water was just pouring down the stairs and escalator there at the aquarium stop. It was kind of unbelievable to see this actually happening. And of course, 2012, after Hurricane Sandy, the Connecticut coast, along with New York and Long Island, and really took a beating. And just looking, back at some of the images for that. This is our locality now and our current circumstances. Our circumstances in our locality have evolved. So just taking a look at the standard of care for architects, it's worth taking a read through this. The architect shall perform its services consistent with the professional skill and care ordinarily provided by architects practicing in the same or similar locality under the same or similar circumstances. The architect shall perform its services as expeditiously as is consistent with such professional skill and care and the orderly progress of the project. So again, our locality and circumstances are evolving. So really, it is on us as architects and engineers to plan for adaptation in our buildings. Every building needs a plan. We need to adapt for flooding, overheating. We need to reduce our greenhouse gas emissions to zero. We need to strategize for future carbon penalties. They're not here yet. They are in Canada. Monte can attest to that, and increasing. We see a preview of this with the local law 97 in New York City, right? Phased penalties for certain levels of carbon emissions from existing buildings over a certain size. That'll be interesting to keep an eye on. In the range of carrots and sticks, that's the biggest stick we've kind of seen to date. And we need to prepare for natural gas bans and retrofit mandates, along with the greenhouse gas emission reduction mandates. That's going to affect natural gas. We've seen that already. Brookline, Massachusetts recently made the news in the last year for banning natural gas hookups in new construction, except for cooking, which we can't seem to get away from, but hopefully we will. And we need to plan to tackle these mandates that are coming, no doubt, in affordable steps over time. So how do we do that? In searching for images of post-Sandy damage, I came across this New York Times article on one family's reaction after the home was damaged, I think in Royton, Connecticut. And this is kind of like an old-fashioned circus oddity to me. I'm kind of horrified, yet I can't look away as an architect. I can't imagine, you know, I don't think this is the answer to mitigation for everyone. I'm looking at this. I mean, they even took the garage up 8 feet with it. I'm curious what the plan is. So, and who knows, maybe someone out there knows something about this project or was involved in this project, but I'd be curious to know more about it. So I don't think that's the solution for everyone. So, case studies. I have a series of more local passive house projects, which by comparison to some of those in British Columbia may seem somewhat primitive, but you know, it's some of our first steps, some of our first generation of projects here in the Northeast. The interesting thing about some of these projects was I personally played a slightly different role in some of these projects. I was the project architect for this project in my previous firm at SGA, who designed this building. So I can offer some perspective on from the architect's point of view, and you know, was in that field trailer at 7 a.m. every Tuesday for a while during construction. So I learned a lot of things from this project. It's a 45,000 square foot building in Norton, Massachusetts at the Wheaton College campus. This is actually the first FIAS certified residence hall in Massachusetts. It's a more contemporary horizontal building in the context of 3 existing mid-century res halls surrounding it. Completes a new quad, one existing space, adding a 4th face to it. And you know, utilizing systems that are not unfamiliar to large-scale commercial construction around here. Steel framing, precast concrete, plank, brick veneer, wall systems, as well as metal panel, curtain wall. This building is sited at the edge of a campus and forms the new face on Pine Street, hence its name Pine Hall. And it provides amenity space for the adjacent 3 buildings, as well as residents of the building. You see on the left a sort of communal space, and on the ground floor and the first floor of residence hall rooms and embedded study lounges on the right. Typical floor plan moving up the building, single and double loaded corridors housing singles and doubles in a very dense fashion. And we can achieve quite an efficiency in cost through density. And the ganged bathrooms here, gender neutral bathrooms, provided an ideal configuration for drain water heat recovery as well, with the gang showers, taking that heat out of the drain water and recirculating it back into the supply. Saved an enormous amount of energy, actually. You know, Monte has a great presentation on pattern language from Passive House, and he highlights many patterns, and a couple of those are laying out mechanical first and centralized ERVs. This particular project, we were fortunate in understanding the need to lay out mechanical first. You know, engineers working with me to take the main distribution down the corridors, of course, as is typical with a double load scenario, whether it's residence hall or other multifamily, and distributing into the units. Centralized ERV was used 1 per wing, Swegan Gold ERV. You can see on the roofscape there with a couple with a VRF condenser next to it for space conditioning, distributed down the corridor into each unit. Also coordinating the structure of this precast plank with its sort of T offset to one side of the corridor so that it didn't have to be crossed with the local flex duct distribution into each unit. Really important to lay out mechanical first. This particular project utilized for heating and cooling a 4-pipe system. So air-cooled condensing units, electric powered on the roof, a gas condensing boiler in the mechanical room. Hard to get away from the 4-pipe system with facilities folks who are familiar and comfortable with that. You know, we could have taken it one step further had we utilized a VRF system and made this closer to all electric. But we didn't quite get there for this project. It's still very efficient. The electric, the cooling is electric, but there's still some on-site combustion with providing heat. One benefit was that instead of fan coil units, we utilized the passive valence system, which are right there at the bulkhead off the corridor in each unit. So at least we could take the fan power out of each terminal unit for the typical residence hall room. You know, it's always a discussion, cost of electricity versus cost of gas as well in Massachusetts. Currently, electricity tends to be more expensive than gas. So, you know, we have a step there to overcome when attempting to remove on-site combustion from our buildings. Other points from Monte's pattern language presentation are highlighting brise soleil. So shading was carefully considered to reduce peak cooling in this building, which is often one of those key targets in larger multifamily projects, that peak cooling tends to be one of the closest to the limit. So with the larger buildings, there's greater internal heat gains from people and equipment, and therefore we don't want to rely as much on solar heat gains, and in fact want to limit them in larger multifamily buildings as compared to smaller single-family passive house projects that you may have more traditionally seen. So in this particular instance, this is achieved in a couple of ways. The typical punch window opening takes advantage of the thick buildup of the brick, basically rain screen assembly, as well as projecting a break metal surround beyond that to achieve about 17 inches of shading on the typical punched opening, which as a 5-foot square was adequate to shave off enough of the solar heat gain to keep our peak cooling under the limit. For taller windows, that same strategy could not be utilized because it did not shade the entire window. With a taller window, it needed a greater projection. So utilizing these aerofoil type shading devices to achieve more close to a 30-inch deep shading on the south and west orientation changes. It's not perfectly, north, south, east, west in the site, as is very rarely the case in an existing urban context. Another one I had the pleasure of working on while at SGA was the Garfield House at Williams College. I was not the project architect on this, but I jumped on and performed a sort of in-house passive house consulting role and helped develop some of the enclosure detailing for this project as well. And this example shows how passive house buildings can kind of take the form of any type of building. In this case, a sort of larger wood-framed vernacular New England type of residential building. So the typical floor plan centers around a large common space. It's a 40 bed building consisting of 4 and 6 person suites. Some inefficiencies occur with a less dense floor plan here. Cost per bed goes up in this suite type of layout clearly versus singles and doubles. And in this case, this was a 2x6 construction, cellulose in the wall cavities, 3 inches of polyiso outboard of the sheathing. It was a fairly cost-effective and simple type of assembly. A SIPS roof provided a simple underlayment for a vented metal roof above, with the again a central ERV system housed in the attic space there, which is within the passive house enclosure. Again, Brise Soleil taking another form here, more of this ladder style of shading device as required over the windows in the south orientation. So other lessons learned include, both Williams and Wheaton, centralized all-electric domestic hot water is still a challenge. Both projects utilized again a condensing gas boiler for domestic hot water as well. This particular project is set up to be swapped out with another potentially all-electric system down the road, so it's all electric ready. At the time, it was quite a challenge to come up with a centralized domestic hot water system locally, and I know we've had other projects that have achieved that, and maybe Monte can get into that with some of his examples as well. This building actually did not utilize cooling, active cooling, and we saw that is possible in climate zone 5 here, but with dehumidification as part of the ERV system. The humidity definitely needs to be managed here, and we saw there was a higher cost per bed in a less densely populated floor plan. Thoroughly broken details are also a bit of a paradigm shift for some subs and even structural engineers who aren't accustomed to that strategy of really keeping every projection outside of your continuous air, water, vapor, thermal boundary. So that took a little bit of coordination. So moving now to our RDH projects, projects that I have the pleasure of currently working on in a consulting role with other architects. This Bunker Hill housing project is being designed by Stantec, who owns the master plan, as well as these 2 buildings M and F, here in Charlestown, Massachusetts. And RDH is playing the role of enclosure consulting and passive house verification, and is also providing mass timber consulting. This is a sort of hybrid mass timber project, as we'll get into. So building M, the smaller of the 2 buildings we're working on, 102 units, 93,000 square feet. Trying to utilize similar details and systems between both buildings, and the larger building, building F, 249 units. And both of these buildings, we're working closely with Peterson Engineering, who is the passive house consultant that had been retained very early on in the design process. And as passive house consultants ourselves, working on the enclosure consulting, we're collaborating closely with them in achieving passive house compliant designs. So another pattern that we strive for in passive house buildings, compact form, and in this case also a relatively low window to wall ratio. Again, and I know Monte has slides on form factor as well, but reducing the surface to volume area where we maximize the volume to the minimum surface area in order to reduce transmission loss through the enclosure of heat is something we strive for. So more compact forms retain the heat we're trying to retain better. So both projects here are pretty good examples of fairly compact form, as well as maintaining a pretty responsible window to wall ratio, and plus or minus 20%. This is also a mass timber project. There's a couple of ways to approach mass timber. In this case, they're utilizing standing panels. They're utilizing load-bearing exterior wall panels. This requires a floor-by-floor construction sequence with temporary wall bracing at each floor. The panels include stud sheathing, air vapor barrier, exterior insulation, and the cladding attachments with leave-outs to come back and lap air vapor barrier over the edge of floor plate and plug that with the mineral wool insulation as well before installing the final rain screen material. So some lifts will be utilized on site here for those leave-out conditions and the final cladding, but this is largely prefabricated with these standing load-bearing panels. And of course, there are challenges with that as well. At the edge of slab, coordination with the structural engineer is required to accommodate any potential shrinkage of the CLT floor plate there, and detailing the exterior cladding needs to account for some of that shrinkage as well, leaving joints for that can potentially reduce in size as well. So again, I mentioned that RDH is performing a mass timber consulting role in this project as well. With mass timber versus other types of construction, even more conventional wood frame construction, we can see that there are different moisture risks for this type of system. The real risk is the top getting wet and absorbing water, but more importantly, the edge grain wicking water, and that that tends to be where we see it. The edge grain at splines are also placed, and the splines being often of a plywood material tend to absorb water faster than the cross-laminated timber floors themselves. So that tends to be an area that needs to see some moisture protection as well. And this is important because on the bottom here, if you lock in that moisture that's on top of a CLT floor or roof, because of all the layers of wood plus adhesive, drying to the interior, to the bottom, takes potentially up to years. So you have moisture trapped in this assembly in a way that doesn't happen in other assemblies. So steps need to be taken to account for protecting the mass timber, both in transport and on site and in construction, as part of the final assemblies to mitigate risk of moisture damage to that CLT. And here's a page from the Master Moisture Management Plan that RDH has developed for this particular project. In this case, this is looking at the intermediate floors and different factors that go into that, where we try to help the design and construction team develop a plan that is integrated into the design and detailing of the project, taking into account products that the team wants to use, that are available, seeing what can be applied in the factory versus on site, and ideally pairing the level of moisture protection to the risk factors, the time and exposure and time of year that a particular project would be exposed to. Another pattern that we look at with passive house buildings are windows with a purpose. Windows serve many purposes. Windows and other fenestration. Designing them for the required views, lights, and articulation of the facade is considered. But window-to-wall ratio also needs to be considered to balance the R value requirements of the opaque exterior assemblies with the glazed assemblies. Windows are a critical component in passive house buildings. So not only do they let in solar heat gain or limit solar heat gain, but they the very design and placement of the windows themselves has a lot to do with thermal comfort and condensation risk targets of the project, and that's something that becomes very important in a high performance building enclosure. For occupant thermal comfort, you want roughly equal interior surface temperatures between glazing and opaque assemblies, and you want that as close to ambient air temperature as possible as well. So, and you can achieve this with high performance assemblies, but when you have a potentially extreme delta between a really well insulated air sealed wall and a lesser performing window, that now becomes the coldest surface and becomes a real place for condensation risk. So high performance glazing selected properly for the project based on the early modeling is important. And also the placement of that is important in the exterior wall assembly. In this Bunker Hill example, it's such a large multifamily project with such high interior gains that the CPHC determined that we could actually get away with as little as 3 inches of mineral wool outboard of the sheathing for FIA certification, which is more climate specific and makes allowances for things like this. But that means, roughly aligning the window with that R value, which in this case is outboard, minimizing thermal bridges around the rough opening as well. So that's something we want to take into consideration just in the very placement of the window within the wall. Looking at that weeding example, you can provide self-shading, but you have to study the ramifications for the installed psi value, that thermal bridging factor around the window opening as well. So I just want to check here. At what point, I know we want to take an intermission at some points. What time are we looking to do that, Anna?
Whatever works best with your presentation, whenever you think.
Okay. Let's finish off these last couple projects that I have, and before we pick up with Monte, perhaps.
Okay.
All right. So again, RDH is playing a variety of roles, particularly RDH Boston, the projects that I'm engaged in. Baker's Place and the Edison in Wisconsin, RDH is really offering our full array of integrated services here. We're playing the role of enclosure consultant, passive house consultant, passive house verifier, And in the case of Baker's Place, we're actually doing lead building enclosure commissioning as well, since we're already out there doing enclosure consulting, and we'll be making field visits and documenting with site visit reports anyway. So this particular project, Baker's Place in Madison, collaboration between Michael Green Architecture and Angus Young locally, client, the Neutral Project, ambitious group of young developers trying to do good. This project, Baker's Place, is a really interesting site with a lot of interesting views to both adjacent lakes as well as other buildings downtown. Really exciting project in general. So again, we saw this image already. That image is actually for this building, for Baker's Place. So we start off with setting our targets for the building to help the design team understand what types of assemblies we're going for. If our window-to-wall ratio is working based on reasonable performance that can be obtained through glazing products on the market in this area. So we look at all these things, and as is typical with a large multifamily project, the cooling load is the closest target, circled here in red. We often like to maintain a 10% buffer on all targets, space conditioning as well as often source energy. And considering that this building has a window wall ratio of about 32%, that resulted in specifying a window with a soil heat gain coefficient for this site of 0.33 with a U value of 0.15. So, those sub 0.2 U value windows, we're getting to for glazing, obviously. And, that's an installed U value. So that takes the spacer, the frame, and opening into account as well. So, these are all things to consider when trying to specify and design a particular fenestration system up front. And building massing and orientation has a lot to do with these targets as well, which is why it's so integral to have these targets set as part of the early design to see, because many urban sites don't allow different orientations for zoning or just simple, massing purposes in a design. This particular building doesn't have any current shading strategy beyond the depth of the opening. So, introducing a shading strategy could knock down that cooling load a little further and give you even more of a buffer. But again, pulling these key levers, when you reduce that cooling load, that can actually increase your heating demand, your annual heating demand. If you limit solar heat gain to a further degree, you're not getting that heat when you need it, potentially. So it's a delicate balance of achieving all of these targets, and subtle differences between PHI and FIAS. FIAS requires you to hit all of these targets, versus PHI, will allow you to take peak or annual. But in this case, we're looking at all of them. So trying to maintain that buffer, get the right percentage of glazing and the right specifications to that glazing, as well as a reasonable R value for building assemblies that are achievable with thicknesses of insulation and reasonable depth cladding attachment solutions. And this is where RDH manages to take it a step further when integrating enclosure consulting, because we understand other factors at play beyond just specifying an R value that may not be achievable in a particular assembly. So in this case, we start off with above grade walls that were R40, but we actually reduced that down through further studies to about an R25, and still making that work, pulling all the key levers and getting it balanced. Below grade walls are 30, floors are 30, roof about R50. So coming up with assemblies that could potentially work and hit these targets. The second building from this client is the Edison in Milwaukee. Same client, similar targets. You know, often you're looking at a site EOI of about something in the low to mid 20s for a multifamily project, particularly in climate zones 4, 5, 6 here, which these buildings are achieving. So interesting site on the river here in Milwaukee. And again, when we look at the modeling, it's a very similar circumstance where the cooling load is the thing that we're having to keep a careful eye on. And actually, in order to get that to work in this particular building, we required an even lower solar heat gain coefficient, 0.24, which is starting to get pretty low. So, you know, again, we have to consider that in the design process. Things that could also help that is potentially GASP, you know, as an architect saying this, but reducing the window to wall ratio further. That could help as well. Further shading could be introduced, but again, at the risk of increasing the annual heating demand. So these are all things we consider early on in the design. And in this case, we're seeing that, you know, we already don't want to mess with too many factors that will affect that cooling load further, because already we have to specify quite a low solar heat gain coefficient on the glazing. And if we want to maintain you know, clear glazing aesthetics without seeing a tint, we can't go much lower. So each building is a little different, having to keep an eye on those key levers. And very similar assemblies here to the previous building, and we reduced the walls down to about 25 based on the studies from the first building. Similar assemblies elsewhere. And in this project, it's also attempting to do a lot. It's attempting to utilize mass timber, prefabricated wall panel assemblies. And in this case, the project started off trying to achieve load-bearing standing panels like the Bunker Hill projects did. But that tends to be quite challenging in construction sequencing versus having your you know, your PLOT and floor slab in place with your non-load bearing exterior wall assembly. So clearly you could build up the rest of the interior and chase it with the exterior wall versus going floor by floor. So this team ended up choosing to utilize, again, a steel frame, a combination with mass timber beams as well, CLT plank, and currently this sort of knife plate detail extending from the top of the CLT to capture with deflection tracks the more curtain wall type of panel. And we've studied numerous orientations as well, vertical panels, horizontal panels. Ended up, you know, with working closely with the fabricator, determining that a horizontal orientation is more appropriate in this case, more efficient, easier to ship. This project started out with potentially targeting blanking now, Michael Green's partner, that panelization manufacturer that unfortunately is no more. So we'd search around for the GC is working with other fabricators at this point. But it's an interesting hybrid system here, and I know Monte has examples that are purely mass timber structure, but it's interesting what we're seeing in the projects in the Boston office. a sort of hybrid approach with mass timber, utilizing other structural elements as well, whether it be a load-bearing coal-forward metal framed wall or more of a conventional steel frame. So this may be an appropriate place to take a quick pause.
Sure. Can we take just like a 5-minute break, and then I'm gonna share some lessons I've learned from the last few projects and some of the things we're working on in some of the larger projects upcoming. So I've got 1 minute past the hour. Why don't we all give ourselves 5 minutes, and I'll start at 6 minutes past the hour on the second part of our presentation. I'm going to try to make time for questions and answers at the end. I hope we have the technology to collect some questions, but let's definitely try to do that if we can. Okay, so we'll see you all back here in 5 minutes.
Okay, sounds good.
All right. I hope people are coming back. Can we tell, Anna? I can't see you or hear anybody or know what's going on.
Yeah, there are people online.
Great. Well, it's a real pleasure to join you today. The sun's just coming up here, and we've had a new snowfall overnight, so it's very pretty world out here in Vancouver this morning. I really appreciated a lot of what Andrew just said. I want to kind of just note on one slide, he talked about the combination of modest window to wall ratio and good form factor. Those are the reasons that actually doing multi-unit passive house buildings and larger passive house buildings is easier than doing single family homes. And so if any of you have kind of come to this first from the single family perspective, or maybe tinkered around with PHPP or Woofy Passive to play with a single family home and found it really challenging, the big surprise here is, for reasons that are kind of obvious, larger buildings can be easier, but they also present different risks and different challenges. I'm going to try to show some lessons learned, starting with this building right here. This was actually the first true multifamily passive house project I worked on. It's several years old now. The first that was finished. We had done some townhouse projects before this and some modular townhouse projects, but this was the first true passive house. And I'm going to go ahead and hang out some dirty laundry and some mistakes we made, so you don't have to make them. Okay, so Andrew, I guess you have the clicker. Can you advance? Is Andrew still with us? I don't have control of the slides here.
Maybe he might not be back.
Okay. If he's not back in a couple minutes, I'm surprised. He maybe have a technical problem or something. Maybe I could share my screen and then I'll just advance them from here. And since we're at the break, we can. You got them? Great.
I got it, Monty. Sorry.
Okay.
Little hiccup.
No sweat. Go for it.
All right.
So this building's called Harding Heights. It's in halfway up British Columbia. We're certainly out of the marine coastal temperate climate that we have here in Vancouver. It's designed by Cornerstone Architects. We've done a lot of work with them. We've probably worked on 15 different projects, passive house projects at this point. A local Yellow Ridge construction. Smith and Anderson was the mechanical engineer, and we did passive house and some enclosure work. It's a very cold climate, as you can tell. This was the day we did the blower door test. It was -20 outside. It was seniors housing. It was 19 small streets. Go ahead. It was a funny design, and it was capable. It was designed to be capable of either modular or on-site construction. The intent was to reuse this design on other small city social housing projects. So they're all, most of them are studios and with 1 bedrooms at the corners. Go ahead. Pretty compact form, nice, simple. It was converted, this shows a slab on grade. It was converted to a crawl space about halfway through, but still great compact form. And notice that tree just to the south of the building. The idea was to use the tree as a design feature to allow more shading in the summer and more light through in the winter. Go ahead. It's a modified double wall. We sometimes call it the ice cream sandwich wall, where it's a conventional 2x6 construction, sheeting on the outside, making cladding really easy. Then inboard of the 2x6 construction, a thick layer of foam, and then inboard of that service cavity wall. Go ahead. So pretty easy to build. You can see this guy here is putting some back insulation into the service cavity wall behind a layer of, I think it's 6 inches on this of EPS foam, and the inside of that foam has a foil facing and makes it easy to tape up the air barrier on this system. The nice thing about the system is you can adjust it for different climate zones by just adjusting the thickness of that inner piece of the ice cream sandwich. Go ahead. Pretty simple mechanical layouts. At this time, we didn't have access to large HRVs. I think if we were doing this building again, we'd probably use 1 larger HRV, but most of our early projects here, simply because of supply chain issues, used household style HRVs like Zenders and household style efficient gas heaters like the sand and CO2 pumps. That's changed over the last few years as the supply chain of larger systems has filled in. And the heating was really simple, just AC base ports because the load was so low. Okay, go ahead. This was our preliminary blower door test, 0.37. It rounded up a bit as they usually do for the final test. But also when we did the blower door test on that really cold day, you know, with -20, sorry, I'm speaking metric here, -20 outside, we remained, you know, what was that, about 15, 16 inside in the range of 60 degrees with that 1 little tiny electric heater heating the entire building. Go ahead. Pretty typical fit and finish for a social housing project. Go ahead. So everybody was happy with the building. It looked good. The construction went fairly smoothly with a couple of exceptions I'll raise here in a minute. Go ahead. It opened up in July of 2018. The mayor cut the ribbon, a bunch of seniors moved in, everybody was full of smiles until the end of the month. Go ahead. When a heat wave rolled in, a heat wave by our standards. So again, that means the outside temperatures were in the high 20s, in the range of 68, 80 degrees. But what was happening was, again, these are in metric, some of the suites were staying hot. They weren't cooling overnight. And we were able to get in, as we heard about this, and get some sensors in, because a few of us happened to be up in the area on vacation. So we mailed up some sensors and started monitoring the units right away. So we missed the peak of the heat, but if you look at like unit 303 there, it's just staying around 30 degrees, which is uncomfortably hot, certainly for people who grew up in northern Canada. And we were trying to figure out why. That dotted line shows what was happening with the outside temperature. And we would have expected to see the units cool overnight as the HRV switched to bypass mode and was bringing more air in. Go ahead. And this caused us to take a deep dive on what caused the overheating in one of our first Passive House buildings, at least during the heat waves. It's performing very well for the fall, winter, and definitely in winter and fall and spring. So the first function was that we had urged the client to use operable exterior shading, such as shown here. This kind of prevents any possibility of overheating to some degree because it's adjustable and easily adjustable for the residents. The social housing provider, which hadn't any experience with it, deemed it unworkable in cold climates, despite the fact that it's almost ubiquitous in Europe and Northern Asia, and too complicated. So it was rejected as too difficult. Go ahead. Our modeling would have showed it would have kept the building comfortable even if. Go ahead, Andrew. You might have to lead me a bit. The fixed shading was just inadequate. Those overhangs, you can see how much light's hitting the large glazing to the south there on all those spaces. And because we're fairly north, the sun's pretty low through the summertime. And so it was hitting for 10, 12 hours a day of heating up. And so it's a huge amount of solar gain. And the fixed shading devices just didn't cover the windows often enough. They were too short, they were too simple, they didn't have sides to them. Go ahead. Furthermore, that tree, you can see it in the middle there, which the architect, Scott Kennedy, actually moved the building over to make sure the tree would shade most of those centerpieces. It wasn't communicated to the contractor that the tree was part of the design. And the first thing they did upon arriving is cut it down and decide to put their work trailer right there because it wouldn't interfere with the building footprint or the parking lot footprint. So that was gone. Now, the key lesson here is that multifamily buildings need exterior shading or mechanical cooling in all instances. Now, I know you do a lot of cooling there, and we're going to come to that. But even when you're doing cooling, the exterior shading can lower your cooling load. And if, as Andrew was saying, you're trying to manage those 4 factors in FIAS, or really the total hits in Passive House Institute, being able to lower your cooling load is increasingly important for all of these buildings. So the key takeaway here is that small buildings like a single family home, the solar gains can easily be 3/4, 2/3 of the heat gain, but in large buildings, they can be as little as 1/3, sometimes as little as 20%, really much, much less because they run on the internal heat gains of what's happening inside the building. Go ahead. And then this was the killer. The contractor found a less expensive window that met the frame specs specified, and that they didn't ask why it was so cheap. And they were getting a quote from a European supplier that was quoting them with no coatings. And so they wound up buying a adequate frame, and they ran those specs for us, and we modeled them and said, yeah, that'll work fine. But what arrived was a window with no coatings at all, and therefore a very, very high solar heat gain coefficient, or G value, of about 0.6. Go ahead, click there. One more time. I think yeah. So what was specified was a 0.4 G value, and what was delivered was, next click, 0.61 G value. Really huge change. And with all that sun that was hitting these windows with no tinting and inadequate shading, we were seeing a huge amount of heat building up on those south-facing units. Go ahead. Then insect screens. So as you can see with that piece of foam that's there, we over-insulated the window frame, as we often do when we use less expensive window frames. We beef up the frame thermal value by over-insulating when we clad. The contractor, as often is done in northern remote communities, ordered independent window screens. The window screens provided by the manufacturers are often kind of cheap, and in the northern communities, they like to put on these really robust, heavy screens to keep out the black flies. The fabricator made some great screens, but they didn't fit because nobody told them the windows were going to be over insulated. So in that first summer, the tenants, to avoid black flies, were closing the windows every night, therefore preventing the ability to drain off heat built up during the day. So their fear of black flies was causing them to trap the heat in the building more than they would have otherwise. And the same thing can happen in an urban community where people are keeping windows closed because there's a lot of particles in the air. Maybe there's smoke from a fire event. Maybe it's just noisy. And so that issue of how people operate it has to be managed in design. Go ahead. And then because the building was designed to be modular or on-site, we had these little mechanical rooms on each floor that could have been prefabbed. All this stuff could have been in a module that arrived. And so it had in a very small space 4 hot water tanks and 2 ERVs right above them. I think, is there a picture on the next slide? Yeah. And what essentially happened was by closing the door and having no ventilation in there, we created a thermal bridge where the waste heat from the water tanks were pre-warming the uninsulated interior ducts and therefore robbing the ERVs of the ability to flush at night. So it's a thermal bridge that wasn't considered a kind of mechanical thermal bridge interior. Subsequent to this building, we no longer put hot water tanks and HRVs or ERVs in the same room. We can all help it. Go ahead. And then finally, the weather was warmer. Go ahead. The average 30-year temperature in Smithers, BC was about 14.2. That was the number that was in PHPP and hourly and other modeling tools. In 2018, August average 16.4. And so we asked ourselves, well, was this an incredible hot zone? So we looked at the years up to that point, and it turned out no. All but 2 of the preceding 10 years were warmer than what was in PHPP. And this got us wondering, how could that be? And of course, what happens is the weather file in PHPP or WFI Passive or any other conventional modeling system, they take a 30-year average, they shave off the peaks a little bit, and they take that from historic weather. And so if you're working in the mid-2010s, you're probably using a weather file that ended, if it's really new, in 2010, or more likely it ended in 2000. And so it was a weather file from 70 to 2000, with the midpoint being 1985. Go ahead. So if the midpoint's 85, to picture 1985, this was when we got Back to the Future, when we had MacGyver. It was a very innocent age now in hindsight. And we realized we were designing Passive House and Step 4, which is a Passive House-like code we have here in British Columbia, for a Marty McFly climate. And we all know the climate has changed a lot since then. And so we realized when we look at like the dashboard that Andrew was showing earlier, and you're twiddling to try to get the heat load and the cooling load just right, it's all bullshit. It's all based on the wrong climate number. All that fiddling is wrong. All of the work we do to adjust and adjust and adjust was off. And this really shook us. Now, the earlier pieces we could manage, but we realized that there's a flaw in all certification programs, code certification programs, or code requirement programs, CS, PHI, in that we're using out-of-date climate files. And so we started after this obtaining information from IPCC and adding it into our files. But we took this broader look at summer comfort. Thanks. Go ahead and click through these. That outside the building, you have solar gain. We're all aware of that. We have temperature, and we're modeling for 2050 and 2080, not 1985 now. You have urban heat island effect, and we'll talk about that in a second. Also, go ahead. Urban heat island effect being, this is Vancouver. Parts of the city are much warmer than others. Same with Boston, same with any city in Connecticut. Where you have leafy single-family home neighborhoods, you have the blue zones, and where you have more urban parts of the city with more concrete, you have these red zones that can be quite a bit hotter, 10 to 12 degrees Fahrenheit hotter is easily. And when the hot comes is at summer nights. And so it really affects these comfort criteria that we saw in Smithers and other places. So we're now considering the fact that most infill projects, which are the projects we tend to do, are in those hotter areas. Go ahead. I think there's 3 factors inside. Occupant density. Go ahead. So the Smithers building, the whole building for 24 apartments is not much bigger than a typical suburban mini mansion, but it had 24 residents in the place that a suburban mini mansion might have 4 residents. It had 21 refrigerators in the place where the suburban home might have 2. 30 televisions to 5 televisions, 20 computers to 4 computers, 60 meals a day to maybe 2 meals a day, maybe even less if they eat out more. So the amount of internal heat gains is really, really different. And again, the modeling protocols address these somewhat, but not fully. And so we're also creating variants around internal heat gains. Go ahead, Andrew. One more, 2 more actually. So to understand overheating, it's important not to just go straight to climate or just go straight to these mechanical things, but think what's happening in this building. And in addition to the kind of things we just showed that we had to adjust after our first Passive House multi-unit project, realizing that you need to look at all of these. One more slide. And yeah, I think this is goofed up a little bit. Couple more. One more. Yeah, here. Most summer comfort modeling is only looking at solar gain and occupancy density. They're not really looking at these other pieces. And if you're not looking at these other pieces as you consider the impact of your building, you're missing it. And so while it's not required for certification, it is, I want to be really clear about this. It is not required. The certification tests for overheating are fairly simple and they use traditional weather files and they don't require looking at urban heat island effect or lifestyle variation. We now do it for all our buildings because, as Andrew mentioned early in this, as professional engineers, we're responsible for delivering a building that people are not going to overheat and potentially die. During our fairly wicked heat wave last summer, we had 595 people died in a 2-day period. Almost all of them were seniors and almost all of them died in their homes. And we realized that during these intense heat waves, that will be the pattern for years. Similarly, there was a lawsuit in San Francisco where a developer was awarded $10 million in a a settlement by a condo association because the building couldn't stay cool enough. It was overheating consistently, and the developer settled to pay $10 million so that the condo association could fix the mess. I seriously doubt that'll be the last of those pieces. Go ahead. So that's our first building. We've moved on, we've learned a lot. And again, our perspective has changed where we're seeing either Passive House certification we pursue as a baseline, as a kit of tools to hit, but recognizing that we need to go better, to be farther, that our need to provide buildings that will perform into a rapidly changing climate means we can't just hit Passive House, and Passive House is not the top of the hill anymore. It's a tool to help us manage all of these adaptation and mitigation strategies. This is a student residence at the University of British Columbia. These are both PHI certified projects. Go ahead. We'll just do a few pictures of this. This is kind of the hallway. It was Public Architecture, a great little firm here in Vancouver. We've done several projects with them. AME Group, a great little mechanical group, and us at RDH. I would note what's happening here is, we're starting to do projects with repeatedly the same architects and mechanical engineers, and it goes faster on your second or third project because you've already sorted things out. This is the entry, fairly typical triple pane glazing, fairly easy to put in. Go ahead. One of the biggest challenges we had was this laundry room because you actually had to pass through it and kind of straddle the middle of the building. And it had conventional dryers. They didn't want to use heat pump dryers or something like that. So we put in, conventional dryer systems, which meant you had this huge outflow of air from each dryer that was just sucking huge amounts of air from the common area. So we created a separate air tightness zone around it. You see those glass doors and glass walls where you can see your laundry in there, but you might come sit outside. And then there's some extra heat being pumped there, and there's more air exchange happening there, but it's separate from what's flowing through the HRV so that the intermittent activity of the dryers, turns out kids tend to do laundry right before they go home. Figure. The intermittent, but sometimes very frequent run of the dryers wouldn't have an impact on the rest of the building. And that's become a strategy we're using on laundry rooms in many places now. Just by creating a separate air zone and a little bit of makeup heat, we can go ahead and use whatever dryers the operator wants to use. Go ahead. The other challenge we had on this building, a little similar to what happened at Smithers, was the windows arrived from a NBC manufacturer and nobody inspected them on site. And it's the same thing that happened in Smithers. And so they were installed with anyone looking really closely at the labels, and they didn't have, again, the tintings that were ordered. They were slightly different window to window. And more importantly, they had a substitute spacer that produced quite a bit more thermal bridging. And we didn't discover this until we went for one of our regular site visits, and we're looking window by window, and we noticed the spacer change. We started going through the labels. If the contractor had simply carefully read the labels against the shipping bill when they opened and uncrated the windows, this could have been avoided. But instead, they had to rip out several windows and replace them in the process, which was, a fairly expensive change. The window maker swallowed the bill. They said, yeah, it was our fault. We didn't ship you what you ordered, so it was on us, and that was good. But we're certainly learning that with these higher performance components, it's tremendously important that someone that understands the metrics of these components opens the box. One of the interesting things about this building, so that's the past house on the left. The one just on the edge of the picture here was built to another green building standard, and the one across the way behind the trees there was built to a LEED standard, and there's yet another one being built to a LEED Silver standard with different approaches. The campus has made a conscious choice to try several green building standards, and they're monitoring them all and monitoring performance of them over time. And so it's going to give the University of British Columbia at Okanagan, this is in Kelowna, British Columbia, the opportunity to build its building monitoring school. They'll be doing this as part of a graduate program and see, which buildings perform better. So we're really eager to see data from that a few years down the road. Go ahead. Are we able to get the video to sound? I'm not sure if we are or not. This is Melvin, who is the architect of the building he's pointing to, which is a 24-unit social housing project in Whistler, BC. And he has a great little chat about it. Let's see if we can get the video to run. Yeah, this is what happened in our pre-show. We can't hear Melvin. Unfortunately, he's giving it a great description, but I think we'll just skip the project and move on to the next one. There's, if you Google the Whistler Housing Authority project, you'll find more about it. But another certified project with some great pieces. Moving to a little bigger projects, and I can't share a lot of images of this yet, but we're working on a 60-story passive house designed by Tom Wright, a guy who's done some really interesting buildings in the Middle East. IBI Group is the local coordinating architect who have done several passive house projects. Integral Group, the mechanical engineer, and us. We're doing several projects with IBI, Integral, and RDH, and it works well. Tom's vision was to create a passive house that does not look like a passive house. That's fundamentally what he wanted to do. He recognized there's a passive house look to things, and he wanted a look that would achieve the passive house standard. He's extremely serious about that, but have a different standout look for a long time. This building will be built with hanging panels on a concrete frame, pre-installed windows, large Swegan, actually ERVs in pairs. They're sistered back to back, and they're just going to fit in the floor to ceiling height. And the actual size of the units is determined by the floor to ceiling height, and there's a few mechanical rooms through the building. It's the tallest passive house planned on Earth. That's 60 stories, plus a few stories worth of kind of atrium and park-like area on the very top there. Go ahead. This is a rendering that was presented publicly, so I could share it as part of our presentation to the city. It recently passed design review, which can be fairly challenging in the city of Vancouver sometimes. That's actually the developer there in the photo in the lower right during this presentation. As you can see, it's got these metal bands that run around. I don't think the brown's going to stay like that, but like most residential buildings, it bristles with balconies and very large windows, but they're single pane. If you notice, I mean, triple pane, but they're one large unit rather than a breaking up. And so there's less frame exposed given the amount of window area than there would be. The total frame on this building still measures like 10 kilometers worth of length, but if you had broken these into small mullions all the way along, it could have easily been double that. And so the management of window design was a huge part of this. Also, all the balconies are thermally broken, despite it being a tension slab. So the tension slab had to be designed carefully by the structural engineer so that it could hold the building together, especially as it bows out and comes back in, but then accommodate the thermal breaks for the many, many balconies. Go ahead. Next to final project we're going to talk about today is the community center. We're doing several of these right now. The city of Vancouver has been really supportive in doing most of its own buildings to the passive house standard. This building is, so the city of Vancouver has taken a very active role in the design. Diamond Schmidt's the architect, and the people at Diamond Schmidt, we've done a few other Past House projects with, Integral Group again, and us. It's a really simple building. You can kind of see from this early sketch, it's basically just 2 floors. There's a daycare on the 2nd floor and a gym and exercise equipment, stuff like that on the main floor. And then just off to the right, out of view, is a swimming area. We're grappling with our colonial history of First Nations here in British Columbia. And so there was a real conscious effort, because this is a park that's being co-managed by First Nations, to create a building that did not look like a residential school, that did not look like this history of colonialism, and to move away from, you know, Andrew pointed out this desire for a traditional architecture in one of the university projects he showed earlier. We have the opposite of that here. There's a real community desire not to look like traditional colonial architecture, which has a very strong negative connotation for a lot of our neighbors. But it's a cool look. Moderate glazing areas, you can tell, and a lot of shading built in. Go ahead. One of the things we're discussing with the city is underground parking. The city, like many community centers, wants it to be easy for people to whip in on their way to work or on their way to take their kids to school, come and use the exercise facilities, hop in their car and go to the next place. But the city is also asking us to model embodied carbon and carbon emissions. And of course, every underground parkade is like an iceberg, where most of the damage is unseen below the surface. And especially when you start doing, this is a mass timber Past House building. Go ahead and click those next 2, Andrew. Those cars become part of the iceberg. They're kind of bombs. Each car contains embodied carbon. The parking space contains carbon. And so there was this real natural tension within the city. Do we want to create less parking to move to this future where we'll probably be far more bicycling and walking and far less driving? Or do we want to put more parking because we're trying to encourage lots of ease of use for residents now? And that hasn't been fully settled. The city's weighing that out. It was interesting that we are actually producing a embodied carbon calculation per stall and saying, great, every stall you commit has this much embodied carbon, begets a car that would probably emit this much, you know, kind of what are the implications per space? Ultimately, we'll do what the city wants to do. I would say for a lot of our mid-rise buildings, especially our wood frame or mass timber buildings, the biggest impact we'll have as planners, as architects, as engineers, is how much we're able to minimize the parking in our negotiations with the city. It may be as important as the Past House itself. Go ahead. We're also discussing internal heat gains, just as we have been with most of our large projects now, because we can't use the presets on these buildings. What are the internal heat gains of a basketball game or a typical workout? So we're making estimates around those, running those past our certifier. Actually, Stephen Winter Associates there in Connecticut is the certifier for this. We have a great relationship with them where they certify several of the projects we're doing here, and we're working as certifiers for some of the projects they're doing in New England. I really like working with them. And so we're working out what these additional internal heat gains are, because you can't really decide the wall system until you have internal heat gains for these mixed use buildings that aren't the typical residence, school, office building. Go ahead. We're also discussing primary energy. Community centers tend to have very, very high primary energy loads. Sorry, again, in metric kilowatt hours per square meter per year. The previous projects at the city had shaved what had been, you know, hundreds of kilowatt hours per year as primary energy down to less than 100. The most recent one, Clayton Community Center, which is also a certified Past House community center in Surrey, just outside of Vancouver, BC, is down about 91, and we're going to see if we can beat that a little bit. PHI will probably set a target in that range of 90 to 130, but our team plan is to see if we can get that out around 80 or so. Go ahead. And then the final project I want to talk about for a few minutes here is the Vancouver Art Gallery. Now, this is a new art gallery building being built on one of the last available sites in downtown Vancouver. It's been designed by Herzog de Morin in Switzerland. Fantastic team. It's been a real delight working with them. Their curiosity and playfulness of how they work is really enjoyable. Perkins and Will is the local architect here. Again, a team that's done quite a few Past House projects. Integral Group, who we work with a lot here, and then us. So it's a team that's done quite a bit of Past House together and has a lot of interest. Go ahead. The building has kind of a donut-shaped ground floor. Again, all mass timber passive house around the outside that would be gated off at night when it's closed. So this courtyard stands around a building with a pedestal that kind of moves out like Jenga blocks above it. So you enter through the courtyard, you exit through the courtyard, and things like restaurants and gift shops are out in that outer courtyard with the main gallery being in the middle. So the intention is to create kind of a fair, also with huge overhangs, because we do have a lot of rain here. And so we want the courtyard to function even on a rainy day with these really, really large overhangs while still being an outdoor space. Go ahead. The building, we're using a tool called Design PH. It's a plugin for blanking on the name of it, that common SketchUp. It's a plugin for SketchUp. This is, a critical design tool we use for a lot of buildings. We're finding it frustrating to use on these very large buildings because we have to remodel. The team works internationally in Revit, where people are feeding to a common file, and that's building in multiple layers week by week by week. And we're having to pull takeoff out of Revit and then model in a separate program. That's delaying our ability to provide feedback with answers like, what if we change this window? Or what if we change this ventilation system? What if we change the floor area in this way? So with this project, we're experimenting for the first time with creating a protocol in Revit where the Revit would have a layer specifically dedicated to passive house takeoff. And it would measure the walls on the outside. Another piece, you want to just maybe go back for one piece there, Andrew? We haven't done it before. It's a little messy at this point. I'm not sure if it's going to make things shorter on this first project. But what we're hoping to get to ultimately is a system where we can do passive house takeoff layers in Revit that would flow into Grasshopper and then directly into PHPP 10, the new version coming out, or Woofy Passive, like either way, it wouldn't matter. And this would give us the ability to provide quicker feedback to large, great design teams like this one, as well as the ability to really quickly, at early design stage, that sort of feasibility study that Andrew was talking about, model the building both ways in PHI and FIAS and give people a sense of what their design would do in each system and what the challenges would be in each system. Currently, it requires 2 whole complete modeling runs, and most teams don't want to look at it both ways. Go ahead, Andrew. If you just hit play on those, I think this is an embodied video. It just has no sound, so it doesn't matter. We've modeled more than 100 details because it's mass timber, passive house, and a very unique cladding system. Because it's using some unique combination of timber beams and other pieces, it produced an incredible amount of new junctions and new details. And we've done woofy or heat 3 models on all of these that are in a database, so that as the design evolves and changes, we can keep referring to the detail number and the psi or chi values in the database and play with the building that way. On larger projects, managing this inventory of details becomes one of the challenges because there's just too much. It's not like a simple building we have 10 or 12. There's just too many to consider. And so managing these pieces is a big part of what we do for the whole group. Go ahead. I'm supposed to not say too much about the cladding, but it may or may not involve a common metal that changes color over time. And it may or may not involve a basket weaving look that's part of the traditional culture of the Coast Salish First Nations here. That will go over a mass timber and concrete structure. Go ahead and click to the next few bullet points. The cladding approach, this technology has never been used in quite this way, so there's some issues we're working through there. There's also a cost issue that may or may not get overcome. The building also has a really complicated program. It has several restaurants, it has a daycare center, it has work studios, it has secure workshops, and get this, the building has to maintain perfect 50% humidity and temperature within 2 degrees Celsius all the time, 24 hours a day, 7 days a week, 365 days a year. In fact, this is a criteria much stricter than the passive house standard. It's an international art conservation criteria. Don't click yet there, Andrew. And that's the whole point of passive house, is easier to maintain that. It's also the whole point of the building. If they can't maintain that, they can't borrow art from like the Louvre or the Tate or other international museums, which is the goal of the new building. And the business plan of the new building is based on being able to bring in these blockbuster shows. And so it's an exceptionally mechanically complicated passive house, and yet one that is considering how Passive House limits the extremes as part of that, and achieving that ability to maintain perfect humidity, whether it's a dry, cold day in winter like today is, or a wet, rainy day in August, and a school buses with 300 kids in raincoats just came walking in, raising the humidity in the building dramatically. So there's a lot of airflow, but not all through the HRV. There's an air handling system, there's a dehumidification system, there's heating and cooling systems, and there's HRVs that run into all of this, all on demand sensors per floor. So it's the most mechanically complicated Passive House we've ever worked on. Now, here's the good news. And what I love about Passive House is we're not alone in this. We don't have to figure all of this out for ourselves, because there's been a few other art galleries. And what I love about the Passive House community is the eagerness to share knowledge as others have done that. And this has been really huge on kind of more technically challenging projects like the art gallery. So among the projects we've looked at are, go ahead, 3 precedents we looked at that are not projects I'm on, but that we've studied in looking at this one. In the UK, there's a Hereford Archive and Record Center. This is just what it says to be, an archive. And that second building in the back has no windows. It's just where they keep records. And they want to keep them at, again, that perfect humidity, perfect temperature. Go ahead. The storage, the workshop area shown on the left, the storage area on the right. The storage area, again, the idea was Passive House will maintain that. When you don't have people coming and going, you can maintain it in the building really clear. This is Elementa Solutions is a great little group in central UK. Next slide. This is the performance data. It's the world's most boring chart. Like nothing happens. It just stays there. But it does it despite outside temperature and humidity, and it does it with almost no systems because the Passive House enclosure makes hitting this target much simpler. Yeah, go ahead and put the other arrow on there too. And so again, we won't be able to leave as much into this in the art gallery because we have so many people, could be up to 1,000 or 2,000 people coming and going during the day. The core idea of using a more resilient envelope to make these sort of standards easier is what's driving the thinking more than the more conventional things about saving energy or reducing carbon. Go ahead. Our next reference building we're looking at and team we're talking to is the Museum of Bavarian History in Germany. 300,000 visitors a year. It's much smaller than our gallery, but it's the largest gallery currently built and has the same requirements of storing things in certain conditions. Go ahead. It's got a classic library or gallery look and feel as you come in. Next slide. It also benefits from being in a traditional Bavarian neighborhood. And so there's these wonderful spots where you walk through the museum and you look out the window and you're looking at, the classic view that they're celebrating in their own culture, in their own way. And so it has that relationship to its community that's really nice. And finally, next slide. They're about Bavarian food and beer. Why wouldn't you be? So they have a fairly large restaurant given the size of the building and a lot of those restaurant loads to be managed. And this is one of several projects, also some large dormitories we're doing in Toronto and in Victoria, British Columbia, where we're managing the restaurant loads and working with restaurant planners to design restaurant facilities that are less taxing on the Passive House requirement. Go ahead. One of the things we're moving to, of course, is induction. The best restaurants in the world, like the French Laundry in California, have moved to all induction. Quite a few other sort of leading high-end restaurants have done so. It's preferred by chefs, hands down. One, it's easier to control, and two, it just makes their lives a heck of a lot more comfortable and requires less ventilation. Go ahead. So induction's an obvious choice. More induction, less gas. Over those hoods, we're putting air curtains and sidewalls to improve the capture efficiency of the ventilation hoods. Go ahead. The higher capture efficiency allows lower flow. And then for the various coolers, especially in these open gallery kind of restaurants or student dorms, everything's closed. We don't have open fridges or open freezers. Everything's got a door and usually a double pane door at that. So you're just not leaking as much cooling out of the rest of the building. In one of our largest facilities, we're also, rather than having independent freestanding fridges that just plug into the wall, we have refrigerants of the size as needed, but they're connected to a common compressor system, so some of the heat recovery can happen. Go ahead. just to put refrigerators in text as a little bit of a side note, the typical American refrigerator consumes more energy a year than most of the African nations' households do altogether. Like that's how out of scale our use is, and therefore our carbon footprint is compared to much of the less developed world. Go ahead. And then the final reference is in Gaobeidian, China. It is a exhibition hall, a museum about passive house. So it's a passive house museum showing off passive house technologies, which is a really interesting idea. You can see the sort of interactive, you can touch and feel things. Everything is there both in Mandarin and English as you work through the building. Fairly classic fins to the outside. You can see how well the outside of that south-facing wall is protected. That combination of getting great light in when they need it and fending it off when they don't makes the design of the building pretty simple. Go ahead. There's exhibits explaining thermal bridging, ventilation, all these kind of pieces. You can move those levers and feel some of the thermal bridging happening through these pieces. It's actually quite interactive and kind of neat in a kind of kids science museum way of being things. I think there's one more slide. Can't remember. Nope. So we've looked and talked to each of these teams and able to learn from them as we do the Vancouver Art Gallery. And I think that's what's really great about Passive House, and I urge you to reach out, is when you're working on something, whether it's your first project, reach out to teams who've done it before, hire teams who've done it before, or maybe it's, in our case, you've done many, many projects, but it's your first art gallery that has to meet this international conservation standard. And so the first thing you do is you talk to other folks who have met it in the standard and consider the options they brought you. Let's move ahead, Andrew. So one more slide, go ahead. I get asked the same two questions about once a week for more than 10 years now. Number one, how much does it cost to build a multifamily passive house or whatever kind of building? How much does it cost? And I often find people think the answer is going to be 30, 40, 50% more over a baseline. And two, what does the project do to my milestones and budgets? Because the fact is, good project managers are constantly watching timelines and budgets. That's what a project manager should do. That's what we do, and as a consultant, it's what architects and everybody else has to do. And so these are reasonable questions. So for the next few minutes, let me kind of just present some data and perspectives on these two questions, because it's where everybody starts. Now, before I do that, I want to note, I'm going to talk just about construction costs here. We all know the actual cost is land cost, soft cost, and operational cost all mixed in. And on almost all the passive house projects we work, the lowered operational costs of simpler mechanical systems and lower utility payments, when amortized after 25 or 30 years, whatever the mortgage is for the building, usually puts these buildings in a positive cash flow situation in the very first year. Like, even if they're only saving a few percentage points on utilities, it's only a few percentage points more in the mortgage. And so it comes out ahead in almost every case. But that's not what people are asking. People are asking about construction costs, so I'm going to answer on construction costs. So this was one of the first studies we did here in British Columbia. It was looking at the first 7 projects in BC. Go ahead and click through the next 3 bullet points there, Andrew. Now this was a mix of both Passive House certified buildings and Step 4 buildings. We have this BC Energy Step Code, similar to the stretch code they talk about there in New England. And Step 4 is the highest step now, but all buildings have to hit it by 2030. And so we step up to it over that time. And so much of what's happening these few years is all of our builders and architects are learning to design to Step 4, either by pursuing several Passive House projects or just going voluntarily to Step 4. But these were the first 7 MURBs we did in 3 different climate zones. And the key thing before I show you the results on the next slide is we didn't know what we were doing. We were all kind of early stage getting into this, and you'll see, go ahead now, there's a link there on the slides. The numbers are all over the map on these 7 buildings. If you just click the circles here, one was 22% more than the baseline, and this was calculated by a pretty good quantity surveyor, and it was 32% lower than the baseline. It's a crazy widespread. Even more confusing, go to the next slide, where the expense went into what systems or envelope versus mechanical versus others, there's no pattern there either. It was kind of all over the place. So the biggest thing we learned in our first study is we didn't know what we were doing. And so you had some teams that overspent and some teams that managed it really well. But the interesting question here is, what do those projects look like F and G, the ones that managed really, really well? Go ahead to the next slide. Oh, it's not here. Sorry, go back. I thought I had put in a slide of it, but I guess not. The slide in the building in Pemberton is a simple double-loaded corridor, simple form factor, modest window size, all of the things Andrew was talking earlier, they had nailed. And by just following all of those little patterns, you know, careful mechanical, early mechanical planning, great process, a team that worked together. It was a developer builder, so there was a lot of ability to work internally. They didn't have to have as many bids out. And a builder that had been building affordable housing for a long time, and their trades and subs were well known to them, and they had long-term relationships with. So there is no one magic to keeping it below predicted costs. It's just good management all the way through. Okay, next slide. So a few years later, the Passive House Network did a look at, I think, 16 or so buildings, most of which were in the New York, New England area. This is May 21, so this is only, you know, not even a year old. And they found first costs between 1% and 8% over baseline. This is about what RDH has seen on our projects at this point too. Most of our projects, they're not as wild as those early days, but the warning here is you might find early day costs are spread out more because of inexperience. And what we learned in this Passive House Network study and a similar study by Passive House Trust in the UK, the biggest thing we learned is the number one factor is the experience of the project design team. It's not what cladding you picked or what ventilation you picked or what windows you picked. It's the experience of the design team manages the costs down closer to 1 or 2% over baseline rather than up around, you know, 8, 9, 10% over baseline. Next slide. And we're seeing that really in New England. Now, this slide came from the Massachusetts Department of Energy Resources, and they looked at these three baselines and saw this very narrow range, you know, 1.4 to 2.8%, 1.9 to 2.9%, or in Pennsylvania, averaging about 1% less. Now, I think the range has something to do with the way public housing is funded in the US. And we're working on several projects, including a mass timber passive house project there in Connecticut. And we, you know, I've learned quite a bit about how these get funded there. And I recognize the funding formula forces you to hit a low budget because you're only going to get so much money. And so they do hit low budgets. And I think that's good discipline. And I think part of what happened with our early projects here in BC is we were projects of various types that were just saying, try this. And so the costs were more all over the road. But I think this is the range that a well-managed, tight team with a little bit of experience is going to find on passive house projects. And this is what we're seeing when we're working, as I showed you in some of those early pieces with architects, mechanical engineers, structural engineers we've worked with before. We're seeing very, very cast house premiums that are within the margin of error. You know, that any quantity surveyor would tell you, yeah, this is, you know, the math comes out at 1.4%, but that could be just high bids, low bids, changing prices. It's been obviously a very fluid pricing environment this year. Next slide. Yeah, these are some of those examples in Massachusetts that are in that last study. Next slide. Okay. So my two biggest pieces of advice for managing down costs are write a really clear owner's projects requirement, and as soon as your team starts, write really clear milestones for your projects. So you want an OPR with specific objectives for adaptation, mitigation, and compliance. It's not just we achieve passive house or step 4 or lead or whatever we're doing and that's it. And don't just say in the OPR, we're going to achieve passive house. Say how you're going to achieve passive house, what your key strategies are. We talk a lot about this in the Pattern Language for Passive House workshop, but you've heard a few of them mentioned today. If a developer or lead architect needs to hire a consultant to understand changing code requirements or changing opportunities for funding as they consider various pathways, do that before you have 10 people sitting around a consulting table at $250 an hour each. That's work that should be done in the OPR, not in schematic design. Figure out what your pathways are, figure out which ones you're going to go to, and actually it makes sense for the developer to issue that in the OPR because you'll get the consultants that want to do what you want to do. If you're vague in your OPR, you're going to get consultants who want to do what they want to do. If you're very clear about what you want, and that's not what a consultant wants to work on, they won't bid. Or if they say, yeah, this is fantastic, this is exactly the strategy I want to pursue, you'll get the right architects, engineers, and other key consultants. So can't stress enough the importance of a clear, concise, not Pollyanna-ish or not overly vague OPR. Next slide. And then once you have your OPR and you're clear, have some good pre-design work that owner's project requirements, hire experienced builders and consultants. If you're the developer or the lead architect, your goal is to be the only person at the consulting table who's not done a multi-unit passive house before, or whatever type of building you're doing. And then once you have put together a team with as much experience as you can possibly buy, and I want to just be clear there, at a minimum, your mechanical engineer needs to have some passive house experience and passive house training. Your passive house consultant needs to have some multifamily training, or whatever the building type is you're pursuing. You don't want a whole table full of newbies. It's going to cost you a lot more. You're going to pay for their training. In a schematic design, we always start with an integrated design chart, unless the teams work together repeatedly, where we, at the very first meeting of schematic design, are bringing a model, like the feasibility study that Andrew described earlier. We're showing the range of metrics the building has to achieve. What might the walls be? What if the windows range is here and the ventilation rate is in this category? So that we can begin talking about specifics on the first day of schematic design, not halfway through DD. Now, because that first energy model is really rough, it's got to have a big buffer. So if your target is, say, 4.75 kBTU per square foot, you do not want that first model to be right at 4.7. You want it to be a good 25% lower, because things are going to evolve. And if your model just barely gets you there at the beginning of SD, you're not getting there. And it's just like a budget. You start with more contingency, and the contingency whittles as you work your way through your energy model. And if you're doing embodied carbon calculations, that model too should have a big buffer at the beginning. This, more than anything else, will save you drama through the whole process. Also really important in the integrated design shred or early in SD to identify the ventilation strategy. Are you going to go with centralized ventilation, real pros and cons to that, or unit by unit in suites? Most often, we find centralized ventilation costs less to install, costs less to maintain, and delivers best performance overall, but not all the time. And there are some builders, designers who are very attached to putting an HRV in every single suite, and so you can do whatever people want. And then to identify the assembly strategy, Andrew showed several options. These could range from full site built to full modular to panelization and palletization of certain parts. What's your strategy? Where you're going? And so it's important to have the constructor at the table at SD to begin that discussion. Okay, moving to design development. The huge thing for the architecture who has not done a passive house for is do the details that matter most first. There's a natural tendency to do the fun details first and put off the slab details that are kind of unsexy until the night before they're due. That will really screw up your whole passive house project, because those unsexy details typically involve concrete or metal, and therefore much higher thermal bridging. And so you're putting off the ones that could really get you, and you really can't afford to do that. So as you saw, as we showed, say, with the museum, we are preparing whole databases full of details to choose from early in the process, so that as the architect is making design decisions, they can see the impact of them. We do therm or heat-3 models of those. Go ahead and key a couple more there, Andrew. We try to identify windows and ventilation systems in design development. Sometimes this requires working around tendering processes, especially when it's a public building and might have very specific rules about how it can purchase things. But we nonetheless try to get the contractor or whoever is managing the tender to have conversations and identify key systems of windows and ventilation early on. You just can't wait until later, because you're designing with those specs in mind. And then somewhere in DD, usually around 50% DD, we do a second energy model that's very different. The first one was all guesstimates. Nothing was actually drawn yet. It was just to set ranges. The second one is now modeling what you actually have and showing some variables. Well, you could change this, you could change that. And a narrower buffer, maybe a 10% buffer at that DD dock. Then moving on to construction docks, it's where the rubber really meets the road. You've got to detail all the models. You've probably sent that 50% DD to your certifier for some initial feedback and some review, checking in on different pieces. I'll say this, we work as certifiers and as passive house consultants. When we're the consultant, we talk to the certifier at SD. We don't want to wait and contact the certifier later. We understand the value, because we're often in, one day we'll be a certifier, the next day we'll be a consultant with different projects. We want to involve the certifier on key strategic questions from the very beginning. It saves everybody hassle. So hire your certifier early should be a key criteria there at pre-design. Construction documents, of course, you're looking for those inconsistencies that can be greater on higher performance buildings, and it's time to start training site supervisors and identifying your air barrier specialists, talking to the managers of the construction team. If they've done projects before, it's not a huge deal, but if they haven't, they need to be trained before they start building on the details that matter. And we try to set rules on the value engineering process so that it's discussed and well understood what the criteria are, what can be substituted, what can't be substituted. So we don't end up with those, window mullion replacements and window glazing changes that just weren't clearly communicated, because those created a lot of problems and drama in the past, and we're trying to avoid that going forward. And it really all comes down to educating key people on the construction team of what they need to be aware of, or at least putting the fear of God in them to think about it and call you before doing something else. Okay, then in pre-construction, we typically do a construction kickoff, like the integrated design charrette. This is typically a full day meeting back before Zoom when we did things in person. There's resistance on the teams to do the integrated design charrette. Oh my God, am I gonna pay 20 people to sit around all day? Same question with the construction kickoff. Every time we've done it, it's saved money. Every time it's not done, people resist it on cost. They end up blowing more than that cost in communication problems. And so there's nothing that will save you more money than getting the key players around a table at the beginning of design, at the beginning of construction, even though it's resisted every time, except by experienced teams who've done buildings before. They absolutely gonna do it. They wouldn't not do it because they see that it actually saves money. Usually that day involves construction mock-ups, training on specific tapes and membranes for that project. It needs to involve some key subs like insulation and cladding and window install subs, and so there needs to be not just the executives, but the people who are actually going to put this stuff together at the kickoff. And so that has to be thought when they're contracted. Yes, you have to attend these as part of this bid. We work out comprehensive QA QC plans. This is one of the ways in which the standards vary a bit. Theus has done a great job of creating checklists and really specific procedures for quality control in the field. And they have the specific person who's a rater who's going to walk through those checklists. Passive House Institute, which has buildings all over the world and probably a greater diversity of type of buildings, recognizes that it's not possible to do all these buildings by checklist. They're built in too many different ways of using consultants, using architects. And so what happens is the certifier asks for a quality control plan and then either says yes or no in that early stage. But we review it, but it's less prescriptive. There's more opportunities for the plan to be done in different ways. And then if you have embodied carbon, it's time to wrap that up too. Embodied carbon needs to be modeled several times as you go, just like the energy model or the Woofy Pass or whatever it is. In the construction, it's like pretty much anything else. Site visits and testing, they may be by the Pass team, they may be by the closure team, certainly by the mechanical team, but who's doing what and who's checking with whom in what order is the key question. Ventilation commissioning is probably what sets Pass House apart from other certifications more than anything else. Contractors are typically scared of air tightness. They can be trained to do that without much difficulty. They should be scared of passing ventilation commissioning, especially if the installers, the tin bashers, can't put everything together really well. Sorry, I've got a call from my son who's sick, so I'm just gonna send him a text really quick here, and we'll get right back to this.
I'll just take this moment to remind everyone we do have a question function on GoTo, so please put any questions in the chat that we can. Yeah,
and we're close to done, so that's a good time to mention it because there's just a few more slides, and then I'm hoping to have a discussion as much as possible. Yeah, air barrier testing, blower door tests, and then at occupancy, it's really important with high performance buildings to do training. Again, kind of like the integrated design charrette and the construction kickoff. important to debrief on lessons learned and recognize on these larger buildings, you have a training for residents, you have a training for managers, and might have a training for people doing long-term maintenance. And all of these people need to be up to speed on what you gave them because the systems often work differently. It's really common, when people build their own single-family passive house, they learned everything during the 2 years they spent building it, or more in some cases. People move into a passive house apartment, they just showed up one day, and it's really common for people to confuse the HRV control with a thermostat. I mean, it's a normal thing. They never thought about this. And so just having simple or not clear about, can I open the windows? When can I open the windows? Of course you can open the windows anytime you want, but here's times it might make you more or less comfortable. So that sort of training is really important on all high performance buildings, whether passive house or not. Debrief on lessons learned. You've heard me share some of the failures of our early buildings here. I could go on like this for hours. The way you save money is by sharing results with other teams, and get out in simple presentations and say, we did this, it was great. We did that, it was awful. We're not doing that again. So understanding as a team where you went right and went wrong, you cannot appreciate how much easier it makes the next project. When we're coming to consulting tables on subsequent projects with teams we worked with before, we know where we did well and didn't well, and we can almost like shorthand right at the beginning of schematic design. Great, we want to do this again, we don't want to do that again, I want to try this on this building, well, I'm not sure about that. An experienced passive house team that's worked together before, that second building is just like any other project. You can make a heck of a lot of decisions the first meeting. Go ahead, I think there's just one or two more here. Okay, you might find this daunting. And for fun, it's great to think about the passive house process a little bit like the hero's journey, as Joseph Campbell and so many have described. So the call to adventure comes in your first project. Wow, I've got a passive house project or another high performance project. You often have a refusal to the call. A big part of every action movie is the hero has to decline to go on the adventure a couple times. And this often comes in the form of developers saying, oh, passive house is going to be too much. It's going to cost 30% more. We could never do that. Somewhere you cross the threshold, maybe you've done the CPHC training, maybe you got your proposal approved. You move on to the trials and tribulations stage of the hero's journey. Often presenting in the form of code officials who are like, what, you can't run ventilation this way. What, this is not enough cooling load. What, you can't put in the window this way. I've never seen tape instead of caulk. Working through code officials who've never seen what you're doing before and is hard. And so educating them and bringing them in the process is really important. There's a despair and hopelessness point where you get your initial review from your pre-certification or your design stage review and you're not passing and you're like, oh my God, are we ever gonna get a passive house? Or you're getting all these change orders back from the value engineering or from initial costing where people are saying, what, you have no idea how expensive triple pane windows are. And many of our first projects, it doesn't happen anymore, but I would say many of our first projects and the first times we started doing more commercial passive house hit a death point, where a bunch of, and it usually comes about the beginning of construction, at the end of construction drawings and tender, where either the constructor or the owner or somebody is saying, I don't know if this is worth it. Do we really want to do this? Should we just build a good building and not try to certify? We had buildings walked away from certification. My first 2 or 3 multi-unit projects didn't certify. They could have, but they just said it was too hard. But many projects did, and they did move ahead, and that was helpful. And then you hit this revelation that you thought way back at the beginning, the way to make the building affordable was to bring it as close to the limit as you could. So if your limit is 4.75 kbg per hour, you want a building that comes in at 4.74, right? Because then you've not overbuilt it. That's wrong. What you kind of realize over time is, no, just design the best building that can reasonably be built and try to get well below the limit. And then if little things slip up or little thermal bridges aren't counted, it doesn't matter. You've got some wiggle room. That whole idea of keeping a lot of buffer in your energy models is the biggest thing you can do to make your life easy, to sleep well, to not have a lot of drama through the project. You have a contingency room in the model. Nothing makes your life easier more than that. And that is also going to save your client money and aggravation. You move along to atonement. There's often in first projects, long conversations with certifiers. It's easier to have these around the circle at the beginning, so don't postpone talking to the certifier. Don't be embarrassed to go to the certifier with what you don't understand or your problems. That's why they're there. So present your concerns as clearly as possible. Again, we do quite a bit of work back and forth with Stephen Winters. On the Marpole project, The moment they were hired as the certifier, like the next day I was on the phone with them saying, okay, I want to talk about internal heat gains, I want to talk about ventilation rates, because we worked on these things together and we're like, how are we going to frame these? How are we going to calculate them for this? Agree on a framework? They said, yeah, we'll approve that if that makes sense. And then we go off and do that work. And they come to us in the same way. Hey, we have this weird building we're doing. We're only doing so many floors of it. How are we going to calculate this? So talk to your certifier early, it'll make your life easier. The road back, you know, you finally get your pre-certification letter or your design stage review letter. It's the same thing in the two different systems. At some point you pass a blower door test, which feels like resurrection. It feels like you're back on. You pass your ventilation test, you pass your blower door test. Everybody's like, wow, we're going to pull this off. This is really going to happen. There's a sense of excitement. And then at some point you've got the plaque you can sort of return with new gifts as the hero coming back from the field. I'm totally serious. Everybody has a hard time on the first one. The second one feels a lot easier, and by the time you're on your third or fourth Pass House project and working with the same people, the same team, maybe not all the same, but quite a few of them, you couldn't imagine doing anything else. And you're ready then to start thinking of Passive House as this baseline on which, great, we're also going to be preparing for the 2050 climate and the 2080 climate. Great. We also have to think about all this flooding. So we have to think about our ground floor really differently and maybe not put any mechanical on the ground floor. You know, in New York, in many places now, it all has to be second floor or higher. Like there's all these new requirements that are not part of Passive House, but need to be considered nonetheless. Do we have one more, Andrew, or is that it? Oh yeah. So as you think about all these, you know, the real limits are adaptation that can include factors like mentioned here, smoke, overheating, sea level rise, depending on where your site is. Mitigation, embodied carbon, operational emissions, waste emissions, upstream emissions, all have to be considered. Again, not part of Passive House. Urbanization, half the population on Earth will be moving by 2070 because parts of the Earth are just going to be really too impractical to live in. Urban populations are growing, the desire to work at home, shelter in place. And of course, affordability is harder every year. Really been hard through the pandemic as we've been watching just rates spiral out of control for a lot of these projects. So there are strategies. You know, adaptation might involve elevating or relocating the project altogether. Go ahead. PV and storage suits adaptation and mitigation requirements. And so if you start to build a Venn diagram, you can put PV and storage in both categories there. Some of the mitigation pieces and affordability pieces, you know, electrification is a great mitigation piece. It doesn't do everything. It's not a fix-all for the building, but it's a super important part of the strategy. Wood frame construction is both a great mitigation source and is affordable in most cases, probably more affordable than other options. Simple form factor, as Andrew mentioned, really important to affordability, but also affects the other criteria. Go ahead and do the next two. Mid-rise rental is a great urbanization strategy and affordability strategy. Urbanization includes things like walkable, bikeable, you know, neighborhoods, less driving, and of course, large apartments. What we're going for here is the best of the Venn diagram. We can't do it on everything, but we're looking for patterns that can be repeated that will force the building, that will achieve multiple things and allow the building to cost less. Solutions that hit more than one of these real constraints. So we're picking over what's worked in previous Passive House and high performance buildings and trying to choose from those checklists and palettes to find solutions that will guide us through this next 50 or 100 years as these real constraints become more and more pressing. And again, back to the hero's journey bit, getting to Passive House doesn't really matter. I don't really care if you do FIAS or PHI or something else, you know, it's a climate emergency, just do something. So getting to Passive House, it's important and it feels good, but it's not the main thing. Getting a building in which people are gonna survive in a world that the IPCC currently guesses is gonna be 2.6 degrees warmer than anything that we have ever had a human live in on this planet in, you know, 500,000 years of human evolution up from apes. That's what matters. We need buildings that are incredibly durable and are going to keep us safe in a future that's hard to envision right now. That's the prize. That's what matters. Survival, both as a species and as an architecture firm or an engineering firm. I think that's the last one. I'm going to remember. We shuffled these slides late last night, so I can't remember the final order. Yep, there we are. So I've tried to push through this last bit so that Andrew and I could answer some questions. I recognize that some of the experience we're having here in Canada doesn't translate perfectly with what you're doing there, but I hope what you see is that we've grown up. You know, we started, it was scary, it was hard, we made mistakes, but building after building after building, we got smoother. Our projects got more affordable, better looking, performed better. And now a lot of this is just kind of what we do.
Awesome. Great.
So Anna, are you going to read questions, or can people read them themselves, or how does this work?
So I'm looking at the questions. I'm not seeing any. Let's see. Let me check the chat. Yeah, everyone in the audience, if you do have any questions, please put them in the question tab that you should see either on your right hand or left hand menu. But right now I'm not seeing any questions. Oh, okay, one just came up. All right, let's see. I work for HUD and have an opportunity to suggest trainings. What vendors or trainings do you recommend?
It's a good question. I think it's valuable early in the kind of growth of Passive House in your community to train as much as possible. I don't know if we can see faces of other people. If we can, that'd be great. So we try to get lots and lots of people from all sorts of, from government agencies, from architecture firms, from engineering firms, as many people as possible through like a good one-day basics course. I know that both PHI and FIAS and Passive House Network and Passive House Accelerator offer various versions of this. We try to have as many people as possible at least have a one-day course to understand how the process works. How is a building certified? What is a Passive House? And then the mistake that a lot of architecture firms made initially is they would have like 2 junior people become CPHDs, but people who weren't involved in discussions about buildings very much, and they'd say, oh, we have a Passive House expert in the office, but really not include them in the critical early decision making. So it becomes really important to have most of the project managers in a firm doing these kinds of buildings trained to get the CPHC or CPHD credential. I don't think there's a tremendous amount of difference between the education of those presenting American FIAS education or PHI education. I think the difference is each one trains you to do their certification metrics, you know? So if you know you're gonna do one type of building or the other, it would make sense to train in that discipline. I also think it's really smart to have in your organization some people who've done the FIAS training, some people done the PHI training, so that you can kind of roll either way. At RDH, we try to have some FIAS experts and some PHI experts in the company sprinkled around so that we're capable of doing whatever our clients might need to do. The interesting thing about the pandemic is training that used to be kind of bespoke and local is now more of a commodity. There's so many people that offer it online. So you can get good PHI training out of the East Coast. You can get it out of Colorado. There's people in California delivering it. There's a group in Ireland that delivers it at a great price point online. There's a guy in Greece who does a fantastic job in English at a really low price point because Greece just has a very different economy. Now, if you take the course from Stefanos in Greece, you're going to get what you need to pass the exam and the basics, but you're not going to get any like construction tips from New England, right? Because you just know that. So there's lots of online courses that can be adapted. Some are recorded, and so find something that suits your budget and your schedule. But I think it's possible to shop around more than it ever was before. Look at Passive House Accelerator, which is kind of platform neutral, has quite a few discussions about training and lists training for different pieces, and that would be a good starting point to look around. But also the FIAS site and the Passive House Network site would also be good places to start as well. And do more than one, learn as much as you can. And then there's some of us, like my course, a pattern language from Passive House, is really designed with a focus on larger multi-unit projects, not single family. and kind of ideally geared for people who've done a little bit education already. They've either done a basics course or they've earned their CPHD, but now they're moving on to a more technical building and they want to go through some of the kind of things we've talked about in this last little bit.
Awesome. Okay, lots of questions coming in. Next would be, when comparing the passive house costs to a baseline, what is the baseline? And is it building COE minimum?
Well, I can answer for us, and then maybe Andrew has a different experience with it. Setting the baseline is the hardest part right now because the conventional cost of anything is changing so fast. Labor costs, supply costs, like buildings are repricing constantly right now. So what the baseline is really hard to tell. It's making these things difficult. And it's been harder these past 18 months than any time I've worked in this industry. When the studies that we did at ZEBEX and the numbers we've done internally at RDH, we hire a quantity surveyor to look at the project in the time period and have data from a lot of other projects that's shared among quantity surveyors, and they establish a baseline using a methodology that's approved by their discipline of a quantity surveyor. And say, great, this is how you establish the baseline based on these metrics, and then you can compare the specific cost from this project to that baseline. The difficulty comes in that when builders assemble invoices, they don't always put them into the neat category that the quantity surveyor wants. And so are these invoices always getting counted in the right category is a bit of the black art of good accounting, and some do it better than others. But I think you have to get a baseline from a professional. You can't make up your own, and you can't use your last project as a baseline anymore.
Yeah, with the local projects, Monte, for instance, the Mass CEC data from Bev, not sure what those particular projects used as their baseline, but I mean, we know where added first costs occur typically, right? We know it's slightly increased quantities of insulation. It's in higher performing windows and curtain wall. Increased quantity of insulation under slab versus code minimum 24 inches from perimeter. We know where these things are. So, in a given project, we can look at those particular items with the CM or estimator, third-party estimator on that particular project. And I actually would be curious to know a little more about some of the baselines from the CEC study, for instance, too.
I think the other thing I'd add on this is these surveys and studies are, general guidelines that can give you a sense of the range. Your project cost is going to depend on how well you manage it and how experienced your team is. So if you're serious about saving money, studying other projects to death isn't going to get you there. It's going to hire people who've done it before, who've worked together before, who are going to avoid these pitfalls and delays and drama that drag things out. And then design a simple, here's the other thing. If you take the same design you did last time, the building that was not a passive house, and you design same architect, the same guidelines, the same expected facade, the same parquet or commercial floor, or whatever else is there, and you say, great, I'm going to take the same thing I did last time, and I'm going to add 6 inches more of insulation, triple pane windows, and great heat recovery ventilation, and an excellent low load cooling system. You're not going to do that for the same price. That's going to be 10% more. I mean, that's how you get to 10% more. You take the old building and you add a bunch of stuff to it. If you want to do it cost parity, you have to design a different building, not radically different in shape, but it's a different building. It has less corrugation. It has better surface to volume ratio, as Andrew mentioned. It has an appropriate window to wall ratio where you're getting great views, great daylighting, great ventilation, but you're not decorating with glass. And you're gonna consider your ventilation options from the very beginning. The architects I work with who really have done this over and over, I watch them. I enjoy working with architects. I really savor and I feel super grateful that I'm able to work with architects around the world now. But I watch how they think. It's one of the things that fascinates me. And the experienced passive house architects, I can see they visualize 2 things right at the beginning. They visualize the shading, the facade, the balconies, not the glass and the cladding, but that outermost layer that they're thinking of, because that's the palette. That's where they can use new materials, new colors, new opportunities. Look at what they're doing on the Vancouver Art Gallery, for example. And they visualize in the middle, just hanging in free space, the ventilation system. Is it central? Is it on the edge? Where does it go? Where am I going to leave the big ducts? How are we going to make this really easy to build in a high performance way? And then they kind of fill in between the cladding and the ventilation system with everything else that has to go in there. It's a little different way of thinking about it, but that simultaneous approach about shading and ventilation as part of the initial concept, rather than, oh, I'll take a glass box and I'll add this. It changes the way they work, and it gives them palettes that I watch them seem to have more fun with.
Great, thank you. Another question, how significant is the overheating problem? Especially in, I think this person tried to say in the northeast of the US. How significant is overheating in the northeast?
I'll let Andrew take a whack at that.
Well, my FIAS training and Ketrin in my ear would say this is a bigger problem on PHI projects, but no, joking aside, I think it's a balance of well, looking at the whole building modeling, and the shading that's appropriate for the particular elevations. The projects that I have worked on to date haven't had overheating problems to my knowledge. I don't know, Monte. What is your experience? You have a greater data set to draw from.
And I do work on projects across the continent, but I work on more projects here in Vancouver. So that's the reality. In my observations, almost all buildings are overheating right now. All multi-unit residential buildings, not necessarily single-family buildings. Everywhere, it doesn't matter where you are. The ones that have cooling, built-in air conditioning, cover it up. You don't know it. You just see it in higher air conditioning loads. And many buildings aren't even tracking their air conditioning loads separate from other electrical loads, so they don't know what they don't know. But I think all buildings are overheating because of all the factors we talked about. Internal heat gains are rising. Local heat island effect is rising, and these are not well calculated. The outside climate is changing, and changing differently. It's changing faster in Western Canada than it is in Eastern Canada. I don't know the spread across the US as well, because we haven't worked with IPCC data there as much. I think what we're seeing in these heat effects, so because the Arctic's warming faster than the rest of the planet, the jet stream is becoming unstable. It doesn't whip around at 275 miles an hour like it has for my whole life, really, and just be really stable, and the pilots can hit it and zip around the way they want to go really quick. It's not like that anymore. It has these big loops that wobble down, because as the Arctic heats, it no longer has the pressure differential to create that nice cone of air. So because the jet stream is loopier and weaker, you get these incredible heat domes where it just becomes super hot down into the States. And these incredible cold snaps are becoming much colder and windier. And what the IPCC says, the IPCC terms and talks terms of predictions. So that what they say is, if you're on the emissions path we're on, the promises we're not keeping, the fact that we're not reducing emissions, by, I should look this up, so I might have this slightly wrong as I'm doing it from memory, but by like 2060, a heat flash, a heat event that might have happened once in a decade previously is now happening like 4 or 5 times in a decade. And by like 2070 or 2080, it's happening 9 or 10 times in a 10-year period. So it's a probability thing. It doesn't mean it happens every year. It just means over a decade, it's going to happen more and more often. And where we're seeing people die or be extremely uncomfortable is during those heat waves. So I think you're just going to see more and more heat waves, and people hit a point where they're so uncomfortable they're willing to do anything to stay cool. And not recognizing in many existing buildings, the building's actually amplifying the heat. Most of the seniors who died, almost 600 here in BC last summer, would have been better off if they could move to a hotel with cooling. But they didn't think of it in time, and by the time you start thinking slowly because you're overheat, you're not actually processing thoughts very well. So you kind of get trapped. So I think as the death toll rises, as the uncomfort rises, it'll be addressed more and more and more. My view is all multi-unit and mixed-use buildings should have cooling. I just think it's not responsible not to. We model them for every building here, and we have discussions with especially the affordable developers, because it's not in their pro formas. They don't know how to squeeze in those extra millions in costs. But as we show them the consequences, they realize, no, I've really got to do that. I'll tell you, in these meetings, when we present our modeling data, including future climate and heat island and others to clients, people usually get angry at me. I mean, I've sat there meeting after meeting after meeting where developers are saying, no, I'm the good guy. I'm doing a passive house. This isn't happening to my building. And we're like, no, global warming's happening to everybody. This is just a physical fact. It doesn't matter who you are or what you are, it's happening. And I watch my clients get angry, and they go through like the Kubler-Ross stages of sort of, what is it, anger, denial, bargaining, acceptance. I might have that out of order, but they go through stages like that over the course of a couple of meetings. And I think that's normal and natural, and I've kind of got a thick skin about it. And so when people want to get angry at me when we present that stuff, that's fine. But the reality is every building really needs cooling now for those heat dome events, and will be critical to have cooling in the future. And as the heat domes get more frequent and more damaging, you will slip to the point where you're out of certification. You can no longer certify the building to the cooling load because the cooling load's rising. And so in those places, it would be good to have passive measures like exterior shading, like a good brise soleil, like great overhangs that are way thicker than 1.5 feet, that are 3, 4, 5 feet on buildings to keep the cooling loads down.
I'll continue that question a little, Monte. Specifically with some of the projects that you've worked on over the years in the very long-standing portfolio, have those instances of localized overheating in the building generally been the result of problems like we saw where glass of the incorrect solar heat gain coefficient has arrived, or site shading shifted from what was anticipated, or what factors have led to some of the localized overheating instances?
Yeah, I don't think we know. I mean, most buildings didn't study it. Like, we studied the heck out of that building because we were really proud of what it created, and we were shocked that it was overheating. We were sure it was going to be fine based on our models. So we looked at it closely, and it's changed our practice. We know there's a lot of overheating in existing buildings. Here in Vancouver, a lot of buildings, like condos, come off the market in July and go back on in September. They don't want to show the unit in August because it's uncomfortably hot, and who's going to pay $1.5 million for an uncomfortably hot, tiny condo? So there's actually a sales season where it's harder to sell. So we know it's happening in lots of buildings. The reason I break down those pieces is so if you're involved in a new building, think about whether they all apply to you and give them some thought. It's a mistake to just attribute overheating to one thing because it is complicated. And as we're doing more renovations on buildings that are overheating, again, we're meeting with stratas or rental owners or commercial owners who come and say, well, we're overheating because of this. And we're like, well, let's test that out first. And before we prescribe a solution, we want to understand why your building's overheating. Otherwise, you could throw a whole bunch of money at cooling when you didn't have to. So we think it's important to understand exactly what's happening through some modeling and some testing, and then design a solution for that will work now and will work in 2050, because that's probably within the lifespan of a good mechanical system or good new glazing at this point. We don't want to throw money away. This is hard enough. Developers take enough risk. Nonprofits take enough risk. We're trying to bring the costs down and the risk down. And so we want to understand exactly what's happening, not guess.
Well, part of the goal of the early modeling and target setting is to try to cost optimize the project, right? Only get what's required integrated into the design to achieve what we need to, and not more, right?
Yep.
Awesome. Okay, another question. You guys are good for time still? For questions? Okay. How do you develop relationships with larger firms, such as Perkins and Will? Do you wait for them to approach you, or do you have a marketing strategy knowing where the city is planning new developments?
Well, that's one reason why I'm here today. Say hello to the architects in Connecticut.
You want to go ahead? Go ahead, Andrew.
No, I mean, so speaking from the perspective of RDH Boston, which is a much smaller 10-person firm that's only been around for about 5 years, mostly working on enclosure consulting first. A lot of people don't know RDH here. You know, I have happened to have worked for firms like CBT and Perkins and Will Boston before. So, you know, I have friends that I'm trying to hit up personally, but, you know, East Coast RDH isn't quite as well known, and we're still trying to establish connections. Monte is in a fortunate situation where RDH is a big player in Vancouver and the Pacific Northwest, and you know, Monte and RDH's reputation precedes him with a lot of projects. So I think it's a slightly different setting here, and I'm sure you've got thoughts on that, Monte.
I am spoiled, so I'm not going to answer for me. I'm going to answer for a lot of my students and people in the community here. So I taught the first several hundred, I don't know, 500 or 600 people to do the CPHD course here in BC. And what I saw in every class is people were forming a network. You know, they were meeting other people in the class and would see them try to chase projects together and work on projects together. And so I think actually taking the CPHD course in person and some of the other courses in person where you can network with the other people, they are starting the journey the same time you are, and they are probably your clients and coworkers on projects. And I have seen many of my students work together, and I've worked with many of my former students. You know, for years here, we had a monthly Passive House social in Vancouver for almost 10 years. And initially we would just meet in a bar, but then pretty soon we had enough projects going that everyone was a project. So we had a mini project tour. So whose turn was it this month? And so you'd show up often by bicycle, you know, and show up at some project of somebody you kind of barely knew that would show up here, bring your own beer, you know, kind of we'll tour the project and stand around and talk, or convene to a local bar. In the early days, I met a lot of my customers through those projects. People who want to do a house or want to do a building would come to see the projects, and we'd get to know each other in those contexts. Now COVID's changed all that, but I think we'll get back to that, I hope, this summer. So I think meeting people through courses, meeting people through socials is a great way to pick up new clients. I think too, you know, watch the large firms that are serious. Perkins and Will in the Vancouver office started doing in-house trainings. They decided rather than send their people to the Passive House Canada courses, they would just hire somebody to come in and do 20, 30 at a time. And I happened to be the trainer for the first several rounds of those. And so I got to know quite a few people there really well. And so it was easy to develop a relationship. And frankly, you know, like a lot of large kind of competitive firms, several of the people who were at Perkins and Will have gone and created other firms or start other firms. So the people in the Perkins and Will classes I taught years ago are now at Diamond Schmidt and Public Architecture and several other places, you know, but Perkins and Will is a breeding ground for good architects with a real green bent here in Vancouver. But it's different in Boston. You know, there's real academic projects focus in Boston. It's different in other places, and so you have to understand what it is there. And then the international architects that we're working with come to me courtesy of the last city planner in Vancouver. So he was fired about a year ago, unfortunately, but Gil Kelly was our planner for years, and there were only so many premium sites left downtown. And as the planner, he had ultimately the power to give extra density and extra height. And what he told every developer was the same. I want you to get an international architect because we want architecture in Vancouver to be more interesting. And I want you to build a passive house. And so developers who had no idea what either one of those promises meant assured him that they would get an international architect and build a passive house. And they got the international architect first, and then they realized somebody who knew how to make that building into a passive house. And we'd been around doing difficult projects long enough that we were lucky that people would come to us when it got hard. you know. And frankly, some of our larger projects had started with another Passive House consultant that ran into rocks, and then at some point we would come on either to support them or take over from them, but then keep them engaged in the project. It's my view that, I mean, it's nice to be sort of in a position where we can pick and choose great projects, but it's better for the whole community if I have lots and lots of competition. I don't want Passive House to be this little thing that a few knights or monks know off in the monastery. I want it to be something that becomes common practice across lots and lots of firms. And to some degree, as you can tell from what we're talking about, we're already seeing as a common practice on which we're adding additional practices around adaptation and mitigation. So it's not the only way to make money by any means. In fact, it's not even as profitable as doing building enclosure engineering and mechanical engineering and some other pieces. But it's a great way to get the opportunity to work with some of the best people at this time in the city you're in. And there's a lot of reward to that.
Yeah, that's great, Monte. I think one of the wonderful things about the Passive House community is their inclusiveness and willingness to share. I mean, that's what caught my attention some 10, 15 years ago when I caught on and started going to the very nascent Passive House Massachusetts annual symposium when it was at UMass Boston, and just blown away by the early practitioners here. Could name drop the typical usual suspects here, but just the fact that they were getting up, showing these great projects, intriguing designs, but had this really comprehensive technical component rolled into the design process, and they were sharing those things that went into it. It was a bit foreign to see designers sharing in that way, and so it's a very open community of designers, and I'll give a little plug for Passive House Massachusetts here. We have monthly meetings as well. They're currently virtual, and we're talking about maintaining some sort of virtual format for those at a distance as we get back into person. So I would invite folks to even outside of Massachusetts to tune in to our monthly meetings, and also the Passive House Accelerator, which has a broader international community. A lot of my Canadian colleagues I see tuned in there too, and just get in there and network with the like-minded people. I'm always excited to meet other designers, architects, CPHCs, and just get excited about what we're all doing and seeing if there's an opportunity to work together. So
I guess the final piece around making those connections I'd add is that as we discussed in this about writing a good OPR and therefore a good RFP, is RFPs have gotten better. 10 years ago, they would say like, well, we want to explore Passive House, really vague. They really hadn't committed. Now we've got RFPs that say, we want to certify to this standard using these metrics. We want to approach these strategies. You must have this much experience to bid on this, So clients have gotten savvy, realized the value of experience, and put thresholds for experience into the RFPs. And when a few of the bigger firms were told they could not bid on a major project because they didn't have Passive House experience, they got really angry. And they went then and trained a bunch of people. We did some trainings for some of the major firms here where we would just do it in-house and have 50 people in the course in their office because they were playing catch up to firms that had been slowly, steadily training 10 at a time. And I think the first time big firms are told they can't bid on a Passive House project, that's when they wake up. That's when they get interested. That's when they realize, oh, I'm losing business because we haven't taken this path. And then the other thing happening here is we have the benefit of this step code coming in by 2030, and many are seeing, it's nice to pursue a voluntary certification rather than a code where if you miss it, you don't get an occupancy permit. Because if you miss a voluntary certification, so you don't certify. It's something you strive for. So many firms are seeing Passive House as a great training path, and many developers are seeing Passive House as a quality path. Because the code keeps moving up, by the time you finish a building, it's out of date. Every single building right now, because the code's changing every 4 years again and again and again, and it takes 6 years to build to buy, plan, and finish a building here. So every building's out of date the day it opens, every single one. And this makes it a little hard for real estate marketers to really communicate where things are. But the Passive House brand, when well communicated, connects with people. Hey, it's quieter. Hey, it has better indoor air quality. Hey, it's more comfortable. Hey, my carbon footprint's lower. My utility bills are lower. My child who has asthma will sleep better. I mean, there's lots of reasons to connect. It's really important to train the marketing people on the truth around that. The problem marketing people have here in Vancouver is they've been saying every single building is the greenest building ever for 20 years. They run out of superlatives and they don't know how to say where we're at anymore. So we have to get them out of greenest ever to specific metrics around air quality, comfort, emissions, and other pieces. And then they can challenge a buyer to compare to the building down the block and say, great, ask them where they're at. And the buyers figure out pretty fast that some buildings are really hitting metrics and others are just saying, hey, greenest ever.
Okay, next question. Are you familiar with any large office buildings pursuing Passive House in North America? And what might be some important differences in the design approach between multifamily and office type buildings?
Yeah, Monte, I bet you have a lot for this. I'll jump in super quick first. Right here in Boston, the Winthrop Square project is going to be a PHI certified project. I believe that's a Stephen Winter project. That is Class A office space, downtown Boston, PHI certified office space. It's a combination of office and residential above. Interesting that they're certifying the office, not the residential, as the Passive House component. And from what I've seen from that project and others, it tends to be, again, there still tend to be high internal heat gains. It's tough in a spec office building where you typically have, curtain wall perimeter or something where you could have a number of tenant improvement layouts around a core. But it's well, a couple things. So I mean, it's again limiting the window to wall ratio. If you can, it becomes having frit and other means of controlling solar heat gain coefficient on the larger percentages of glazing you probably see on that type of building versus a multifamily building. Shading devices, if you can, that's always a conversation with window washing strategies. Ventilation and mechanical, that's an interesting conversation. I mean, that what is base building, what is the tenant responsibility, that has to be thought out and probably put into a tenant agreement ahead of time. Is there a common building ventilation strategy that you plug into rather than the building building air, like on if you have package units or something? Monte, what else are you thinking about?
Winthrop Square is one to watch, absolutely. Lois Arena and her team at Steve Winter Associates with Passive House consultants on it, but we talked to them a lot, so we're hearing about it a bit. It has had several rounds of review by PHI and ongoing issues that are typical for office, and so I think it's going to set some new standards for offices and make it easier to do in the future. We've gone through this funny period in Vancouver where when we first started doing Passive House, we actually had kind of a glut of office space and a severe housing crisis, so there weren't a lot of offices being developed. By 2018 or so, we had a clear shortage of office, and there were a lot of teams trying to do office, and they all had the same idea. It was really bizarre. We were on like 7 or 8 projects that were all basically a 6 or 8 story mass timber building in a glass box. They just all got to that same design. It came again and again and again and again. And it was difficult because it's hard to make a glass box a Passive House. And they're really hung up that they wanted to show off the mass timber and have this glass wrap around mass timber, and that would be lower in carbon. And they really didn't like hearing, no, actually, this is a carbon pig. The operational carbon of a glass box offsets the carbon, embodied carbon gains of the mass timber by a huge margin. And so we lost some of those clients because they didn't like what we were saying. We suggested others go with step 3 in the step code, which is currently a pretty good standard. It could be met very easily. And then we had several that were moving forward, including 2 to Passive House, but then during the pandemic, they're all on hold because nobody really knows what's going to happen to the office market out of the pandemic. So all of those that didn't yet pour any concrete in the ground are just iced, and we don't know what's going to happen to them. They could come roaring back. We're having a lot of tech companies moving to Vancouver and film companies. I think we're going to have to grow out of that wood building in a glass box fetish because it's just way more cheaper to do if you have a different glazing ratio. And the other reality of offices is to accurately calculate the internal heat gains, you have to know the density. And offices are way more dense. There are way more people per square meter than they used to be. And so some of the traditional, like the standards that are used as presets don't work for them. So on our office projects, we are calculating internal heat gains based on the number of people and the actual equipment in the building, and then using that to design cooling and heating systems. They are cooling dominated in almost every instance. So they're more like the community center and the art gallery that we showed in terms of how we approach them. And then finally, what I hear from planners is the next big thing is, more aggressive mixed use, like Winthrop Square is a good example. That building has residential, hotel, office, and retail. I'm not sure if that's exactly the sequence, but all in the same building on different floors. And in that project, they're only certifying the office. They didn't want to go after the residential and hotel. It might have been easier to go the other way, but it's still a starting point. And what we've seen before is that once a new building typology achieves certification to either standard in a region, a bunch more follow. So having that first big one, like Winthrop, probably will shape it, assuming there's market for new office space. It's not hard though. Offices don't have balconies. The window openings are fairly easy to cope with. And the internal layout is pretty much designed. They know the density. So the calculations are easier than mixed use or community centers or local gallery, stuff like that.
The challenging thing in this market in Greater Boston is the lab building. We have often lab office, some split 60-40 lab office, and labs, depending on the exact program, are a bit of a wild card, aren't they? It's mostly ventilation rates on things like hoods. So it changes the equation a little bit, right, Monte? I mean, so that's something.
It does, and this was actually RDH's problem in obtaining. We're leasing our office space here in Vancouver, and we have a lab on the ground floor to do a bunch of testing that had to build a huge hood because we have various toxic tests happen, and an office space with other companies in the upper floors. It's very hard to find a building that has both lab and office space, and it's been a challenge for RDH. The Waterloo building is actually at the university. It's all lab. There's no office. It's just a sprawling lab complex. So yeah. We deal with that internally as well.
Yeah, well, often, around here, we'll have a split by floor, half lab, half office on the floor with a particular tenant. And that presents some new challenges as well that need to be worked through with mechanical engineer on the team as well. And, I could speak a little bit for FIAS too. I mean, that standard continues to evolve a little bit as well. FIAS as an institute, I know, is willing to work with teams as well, and perhaps continue to modify the standard and make certain allowances based on new program types. As we try to apply this level of performance to a more broad set of buildings and programs.
Yep. Yeah, I think that's an important point. The standards are diverging more with each passing year. My connection to PHI started before FIAS existed. In fact, Katrin was a PHI person at that time. So, many of us just started with PHI and kept doing it. And it wasn't ever a choice between one or the other. It's like you work with these people, you've known them for years and years, you just keep doing it. When FIAS initially started, it was essentially the same as the PASFA standard. It was half a dozen little differences, but each year, each revision, FIAS made good efforts to try to bring itself more in sync with specific American standards and funding targets and other things to make American projects easier, and to kind of collaborate things for American-focused projects. And I think they did well at that. Whereas the international standard is trying to come up with metrics that work in Greece and Spain and Italy and Canada and Australia and China and everything else. And they're constantly balancing tug of wars because we're all asking for different things at different times. So they've evolved differently, and I think they get a little more different every year. And that's good because, you know, we're in a climate emergency. We need to retrofit billions of buildings. We need to build new buildings much better. It's good to have multiple pathways. It's good to learn from both. I think both organizations are struggling to figure out some of the issues we've raised in this little presentation. And frankly, so is Living Building Challenge, you know, and other Powerhouse and some of the other pieces. So I am an advocate of anybody pursuing these projects seriously in any standard or system, and critical of those who are not. So just pick a path and go for it.
Yeah, and I think with PHA projects too, there are numerous great examples of passive house office buildings in Europe and beyond. One of my favorite firms, A2M, right? Sebastian has fabulous, well-designed projects, and many of them are office buildings and other programs beyond multifamily.
Yeah. So, Anna, can you pick one more great question from whatever you got on the list?
Yeah, since we've got only a few minutes left. I guess the last question will be, do you feel that historic preservation is a hindrance to passive house?
Can I feel this one, Andrew?
Yes.
No, I don't. I don't think it's a hindrance to passive house. I think in the wrong hands, it's a hindrance to cities. And let me explain that. PHI has had a retrofit standard for more than a decade. And it's always allowed exemptions for places where you actually have historic fabric on both the inside and the outside of the wall. In other words, you can't insulate to the outside and you can't insulate to the inside, or you have an amazing window or an amazing door. Now, there's very few buildings that have that all the way around. So you see many of the historic retrofits in Brooklyn and others, which are very expensive buildings at this point, will preserve certain aspects of the front that are worth preserving. And we just make exceptions for the thermal bridging. We make exceptions. We counter the potential condensation with airflow or heat inside. We just make exceptions. We just say, yeah, it's there. But the criteria is, and this is the criteria from historic preservation experts, is that means you've got historically valuable fabric on the inside and the outside of the wall in the window, right? Otherwise, you could insulate one way or the other. So real historic preservation, I don't think, is a conflict. That said, I also don't think every building has to be a passive house. And if there were an extraordinarily historic building that you just wanted to leave as it was for that value, why bother? I think the 90% of average buildings should be passive house. I also think there's beautiful, I think of like the new Bath station in downtown Brooklyn, at the site, the one that looks like a bird, there's extraordinary buildings we do from time to time. But just, why bother them passive house? Just let them be beautiful, let them be incredible works of art. But the fact is, the vast majority of our buildings are fairly bread and butter, and they ought to all be passive house. So I wouldn't get hung up on it. What I do see, at least here in Vancouver, is that not in my backyard groups that are resisting housing density use historic preservation as a wedge. And they're grabbing on to certain historic things that are not actually historic in the sense that the actual preservationists would have scorecards and ways they consider historic value would say is historic, but they want to seize on it as a reason to block housing. And it has nothing to do with passive house, but it's becoming a problem more and more and more. And we're unfortunately seeing NIMBYs posing as preservationists pitch preservation versus energy efficiency. and it creates a really unhealthy dialogue, and trying to figure out how to make that discussion more neighborly and more productive. I wish the question and I could go back and forth. I read the one-way channel because I'd actually love to hear more about that.
Yeah, I mean, I have some thoughts on that too, Monte. I mean, I actually sit as commissioner on the local historic district commission in the town where I live in Swampscott, Mass. So, you know, I'm familiar with local HDC practices, at least in the Commonwealth here, and appreciate aspects of preservation as well. You know, I've yet to see, unfortunately, a proper deep energy retrofit come before us. I'm waiting for that day. But yeah, I mean, passive house shouldn't be forced on every single building, and not every building is the right candidate for it either. But we can do things that make that building perform better, and we know what those things are. It's a balance of mechanical and enclosure, and certain things can be done with enclosure to historic buildings, perhaps on the interior. Lots of factors to balance there, and of course, you know, air tightness is an issue with passive house that sometimes is a challenge in existing buildings as well. But I mean, you know, some buildings are worth have notable historic components that are worth saving and not cladding over, overclad. And you know, but there are lots of buildings that an overclad wouldn't necessarily be a detriment to the character of that building. You know, what is the stat? Something like by 2050, something like 80% of the buildings that will exist are already here. So, you know, as far as decarbonization, we've got a lot of existing buildings to deal with, and that's going to be a major step forward. In fact, for our Passive House Massachusetts group, that is the theme of the year, is retrofits to existing buildings. So we're hoping to take a closer look at various retrofit strategies, some of which deal with more historic buildings and commissions. We had an interesting presentation this past month, actually, about including some projects in Connecticut that wind development had worked on, the Tyler School, for instance. So yeah, there are challenges, but you're right, Monte. It shouldn't be a wedge. Historic shouldn't be used as a wedge.
Well, let's leave it there. I'm really sorry that I don't get to meet more of you in person and have cookies and coffees and chat more after this. It's a pandemic limitation. I might make it down there in June for the Passive House Network Conference in Boston or somewhere down the road. So I hope we can meet some of you in the future. And I wish you a lot of luck with whatever you pursue.
Thank you so much, Monte and Andrew, for this great presentation and spending 3 hours of your time on this. It was a great presentation. I just want to do a quick shout out that there is going to be a Connecticut-based fee CPHC designer consultant training in April, and there will be weekly Q&A sessions. So just getting back to the networking, that would be a great place to network. And so registration is up for that, I believe. But yeah, well, we will wrap this up since it's 3 minutes past noon. And thank you guys again so much for presenting today.
Thank you very much.
Thanks, everybody. Thank you, Anna, and everybody helped put this together.
All right. Have a good one. Bye.
Take care.
Thank you.